Hello, welcome to Convergent Dialogues. This is Xavier Bonilla. Okay, on this episode, I am very pleased and honored to have the extremely brilliant Karl Friston. Karl is a theoretical neuroscientist and pretty much one of the major authorities on brain imaging. He's a professor at the Institute of Neurology at University College London, consultant for the National Hospital for Neurology and Neurosurgery in the United Kingdom. He has invented many aspects of brain imaging, including the Statistical Parametric Mapping, Voxel-Based Morphometry, and Dynamic Causal Modeling. Much of these were used in schizophrenia research, which we talk about. He talks about this in terms of his day job, and then he has his kind of weekend job, which is trying to find these theoretical models and structures of the human brain. And one of these theoretical neurobiological models is what he titles the free energy principle, which we talk much about, which also has some connections with the Bayesian Brain model. He is a fellow of the Royal Society of Biology, and he has many honorary doctorates. And we have a wide-ranging conversation about many, many, many topics. This conversation is over 3 hours, and I was absolutely, privileged to get over 3 hours with him. He was very generous with his time and his energy and his mind. And we talk about everything. We first start by talking about the history of models of the brain. So over time, there have been many models of the brain, and so he gives a history of what that looked like. We talk about the evolutionary components of the brain and how executive functioning and abstraction work with various organisms. We give an overview of the Bayesian brain. Talk about predictive coding or Bayesian filtering. We talk about the two classes of neurons for prediction error and for predictions. He gives a very, very nice, comprehensive explanation of the free energy principle. Talk about the importance of a Markov blanket and the importance of equilibrium and homeostasis. We talk about the free energy principle and a little bit of Freudian psychoanalysis and some of the connection there. We talk about his views on consciousness and how active inference is in play. We talk about AI. We talk about the various neuroimaging techniques that I mentioned earlier. We talk about fMRIs and some of their challenges there. We also then end towards the end of the conversation with how the free energy principle could be used pragmatically. I have to say, this conversation is it's long, but it's very engaging. I found the conversation to be very engaging, and even though it's pretty dense in some areas, I've found it pretty easy to kind of track and follow along. So, Karl does a really nice job of explaining very hard and difficult concepts in pretty easy to understand ways without losing the integrity of the concepts. And so it definitely requires some attention because these are some really complicated ideas. But I think it's super important. He's doing really important work, both in his day job and in the imaging for the brain, and then also his weekend job, as he says, for trying to understand a theoretical framework and to understand that the neurophysiology and neurobiology of how things work together and how this can interact with engineering, AI, kind of computational neuroscience, neuropsychology, etc. So again, it was an absolute honor and privilege to have him on the podcast and to give me so much time and energy. And so I'm very pleased to bring you Karl Friston. I'm here with Karl Friston. Karl, It is a big honor and a privilege, sir. So I thank you so much for coming on the podcast and being willing to talk to us about your very important work and all of the things you've been researching. So big thanks to you.
Well, it's a pleasure to be here. Thank you for asking me.
Of course. So for folks that don't know who you are, kind of give your potted biography. Just give us the snapshot of who you are, what you do, what you study, and all the particulars.
Right. I have my day job, and my day job is a professor of neuroscience at University College London, with a special expertise in human brain scanning. So I originally trained as a psychiatrist and got into the field of imaging neuroscience in an attempt to understand disorders like schizophrenia by literally looking at the brain as best we could or as best we can using modern technology. And then I have a weekend job, which is more of a theoretical neuroscientist. And latterly, one could generalize that to being a theoretical biologist or a biomathematician, trying to understand the fundaments of sentient behavior, the principles that underlie the way that we make sense of the world, that informs and is informed by the day job. So the more you know about what the brain must be doing, the more you can start to look at the empirical results from the brain imaging and understand the message passing and the fluctuations in neural activity in the service of sense making.
Yeah, no, that's very, very important. I guess I do want to ask you about the imaging piece. How did you kind of, stumble into this kind of way of doing the day job and the weekend job? This is something that you mentioned you were trained as a psychiatrist, but was this something that you always wanted to do? You were always curious about the brain and looking at different ways of understanding its functioning? And then did the theoretical stuff kind of come later? Or how did this kind of, morph into where you're at now and what you're currently doing?
That's an excellent question, which I could answer quickly or take a very long time answering. The quick
Whichever way you want.
Let's do the quick one.
Okay.
Now, I always wanted to do this. So what I am doing now is really the denouement of a series of serendipitous and lucky career choices that actually started around the age of 15, wanting to be what in those days would have been known as a mathematical psychologist. So a dual commitment to understanding the most interesting thing, which of course was me and my brain at that time and other people's brain, but using a formal calculus, your principled approach. So trying to maintain a training and investment in physics and mathematics, a sort of dual early career in psychology and physics, and then went into psychiatry as the most alluring and, I have to confess, the easiest way to become a medic at that point in time, because everybody else wanted to be a heart surgeon at that time. It comes and goes. Everybody wants to be a GP nowadays, but my cohort, they all wanted to be heart surgeons. But I ended up in psychiatry and very much valued that experience. But of course, it was exactly in the direction of travel in terms of what I ultimately wanted to do, which was research into what would nowadays, I guess, be thought of as theoretical neurobiology or computational neuroscience, but essentially the formal principles that underwrite our ability to engage with the world and make sense of that world.
Yeah, it's interesting the way you put it, because I think that finding out kind of how you, as you say, there's this serendipitous way of falling into these things, which is, I think, kind of true for a lot of people, right? They have a one way in which they want to do things when they're younger, and then they take the long way up the mountain. But the other thing is having a desire or passion to want to do something, to understand the brain, and many people want to understand the brain, but then having the IQ points and the capacity to do that. I mean, you've written some pretty prolific papers, and so, having the ability to do the equations, to do the math, to be able to do these things, that had to all of just, when it kind of fit together, had to have been pretty remarkable, I guess, for yourself to be like, you know what, I have this interest and I can actually cognitively do this. I can figure this out. What has that, I guess, just been like as you progress, through your life and be like, you know what? Yeah, I've done a few things. I've researched a few things. I've figured some things out about the brain. Well, if you kind of look back on that, how does that just all kind of sit with you, I guess?
I would imagine it's the same kind of sense that people have when they look back on their lives. It's a long journey. And when you look at the journey in retrospect, you are sometimes surprised by how far you have come. But of course, in pursuing at any one moment in that journey, it all seems very incremental. So it seems unremarkable during the travel. Unremarkable in the sense that things change quite slowly and are the reflection of the way that you've invested in the early parts of the journey. So coming back again to this early commitment to a formal way of expressing ideas. So knowing that meant that you had to spend many years learning quantum physics and probability theory, which then you immediately forgot as soon as you went into psychiatry. But at least you left with the legacy that you knew you could learn it and you could do it if necessary. And of course, in later life, it did become necessary. But I repeat, I'd forgotten everything I learned as a 20-year-old. But with the boon, the gift of Wikipedia, I was soon able to get back up to speed again. So all of this prolific writing that is often claimed to be quite inscrutable and mathematically difficult to access. From my perspective, is a nonsense. You can get all the maths you need from Wikipedia, because that's exactly where I got it.
The power of technology is remarkable in many ways. So that's great. So obviously, I want to get to your main, I guess, theoretical claim to fame, if you will. I mean, there's many claims to fame, but I definitely want to talk about the free energy principle and just have you download that for us and just tell us everything about it in as much detail as you'd like. I figure before we get to that, it might be helpful, and you can tell me what you think of this, it might be helpful to kind of look at a history and overview of various brain models that we've had. And how leading up to the current brain model that we know, and then we can branch off to that into the kind of Bayesian brain model, which is also more relevant and salient at the moment. So maybe if you could just, from your viewpoint, how do we understand a history of various brain models? Where does it kind of first start and originate? And you can just kind of march us through how that gets us to current day and what the current brain models are.
Well, yeah, in fact, that would be, I think, one fairly comprehensive and complete way of understanding the free energy principle, which is just a denouement of a long legacy of ideas that I think you could probably trace back to the students of Plato and shadows on caves and the like. But for me, most clearly articulated by Helmholtz in the 19th century, a sort of polymath who had a deep understanding of physics, but also perception and various aspects of sentience. And many of his ideas essentially summarized in the form of unconscious inference. So the notion that the brain was a constructive organ that was inferring the causes of its sensations. So the idea here is that what is out there is not directly accessible from the skull-bound brain, but has to be hypothesized. You have to have the cause of your sensations in mind in order to use the sensory impressions upon your eyes, your ears, or your skin as evidence for or against that hypothesis. So as Andy Clark would put it, this is very much an inside-out approach to perception, as opposed to an outside-in view, which actually dominated in the 20th century, but then went away again, where the world impresses itself upon your sensory epithelia, and you somehow extract information from that to get to the conclusion, oh, this is the cause of my sensations. Helmholtz had a much more nuanced and veridical, or certainly by 21st century standards, veridical understanding of the mechanics of perception, where you had to actually generate the hypothesis and you just used the sensory evidence at hand to update your beliefs, adjust your explanation for those sensations, and in that adjustment and in that updating on the inside through neuronal activity, you were able to produce an approximate or partially faithful reproduction of what could have caused your sensations, and he called that unconscious inference. That notion remained in abeyance through 20th century behaviorism, manifesting in many different ways. Things that come to mind include analysis by synthesis. One key contribution from psychology was the notion of perception explicitly as hypothesis testing. This is Richard Gregory, a UK psychologist's notion. Again, reiterating the importance of inference. So for Helmholtz, it's really unconscious inference. For Gregory, it would have been, the perceptual act is basically a test of a hypothesis that this visual object is the best explanation for this pattern of sensory impressions, say on my retina. Those ideas came to fruition in machine learning and computational neuroscience in, I would imagine, the 80s and possibly the 90s, probably best exemplified by the Helmholtz Machine, deferring back to Helmholtz's original ideas by Geoffrey Hinton and colleagues and Peter Dayan and colleagues. So leveraging those deep insights from Helmholtz and then putting them into a recurrent neural network or a network of a particular kind, a kind of Boltzmann machine, effectively training neural networks in a way that we would now understand the training of deep neural networks in deep learning, for example, to infer. We now understand that as amortization. If you were in machine learning, it would be this notion that you can train the connectivity of a neural network to make sense by inferring the causes of its inputs, because it's a simple move to understand this scheme or algorithm of the Helmholtz machine as also applicable to neuronal networks. And at that point in time, people were converging on very similar ideas from a slightly different direction, namely that of predictive coding. So predictive coding was originally devised in engineering as the most efficient way to compress sound files in the 1950s. And there's an interesting connection here between the notion of compressibility and efficiency and the statistical efficiency of a good inference, which we may well come back to later in the conversation. But at this stage, in terms of the history and the legacy, there was in the 90s then a key convergence on the brain as an inference machine and the brain as a predictive machine. So we then see the emergence of predictive processing or predictive coding in particular. Perhaps just for your listeners, just to make this a bit more explicit, the predictive coding is defined in terms of a scheme that is trying to resolve prediction errors. So we have this notion now of the brain generating top-down predictions on the basis of its currently preferred beliefs about the state of the world. Those predictions then compared with the sensory input, and then the mismatch or the divergence between the predictions and the observations, the sensory samples, are then denoted as a prediction error. And then that prediction error is then broadcast deep into the brain's hierarchy to update and revise the hypotheses or the representations that are generating the predictions. And I use the word generation there because all of this machinery, all this message passing with sense making comes under a particular generative model that is entailed by the architecture of the brain. So you have this picture now of the brain broadcasting from the inside out, descending down the hierarchy, its predictions, and there's a counter stream of ascending prediction errors that are revising and updating the the predictions in virtue of changing the representations that can also be cast in Bayesian terms as Bayesian belief updating. So now you've got another church of mathematicians, theoreticians in the game. You've got the Helmholtz machine, you've got predictive coding people from engineering, and also people like Simon McLaughlin and Raj Rao and Dana Ballard noted that these predictive coding principles were very apt to explain a lot of the functional architectures of the brain. David Mumford, I think, was a key contributor to those ideas in the early 90s, and is not usually acknowledged as such. But if you go back in very early 90s, a very explicit and what proved to be a visionary account of the neuronal architectures that did the job of the Helmholtz machine, that did predictive coding, did hierarchical Bayesian inference. So then you had the joint emergence of Helmholtz machines and machine learning, the Bayesian brain hypothesis in the neurosciences, and predictive coding as a particular process theory that sort of enacted this. So that was a story at the end of the 20th century, at which point there was an inactive turn, a turn back to the 4 E's, the importance of situated cognition, the importance of the fact you have a body, that your perception is an active thing. You actively palpate the world at every level, at every sensory modality, whether it's literally feeling your way around a dark room to confirm your hypothesis about this is a telephone, this is the bed, this is my iPhone, through to palpating the world visually through active vision, moving your eyes around, sampling this part of the visual scene to test this hypothesis or that hypothesis. So this embodied, inactivist, extended, and by extended here, one's acknowledging that a lot of your cognitive abilities are downloadable into the environment. The key thing here, though, is this inactive term. So how did predictive coding, the Bayesian brain hypothesis, survive the inactive turn? Well, very, very simply, that there are 2 ways that you could effectively resolve your prediction errors. You could either literally change your mind in the good old-fashioned predictive coding way, you use your prediction errors to drive a change of mind, a Bayesian belief updating, so that the predictions now were more fit for purpose and explaining away the sensory inputs, and thereby the prediction errors effectively cancelling themselves, resolving themselves through this hierarchical message passing in the brain. Or, and here's the twist, you could literally go and resample the sensory input to make it match your top-down predictions. So now you have a really simple and very plausible account of active sensing, active vision, more generally active inference. There are 2 ways in which you can resolve prediction errors. You can either change your mind or change the thing you're predicting, and thereby supplying the predicted outcomes. So this is a very simple account of action and perception, and also speaks to the circular causality. These are 2 processes working hand in hand. Your perception is causing action, and action is causing perception, and this is how we sense make. So that sort of active inference perspective, which then I think became sort of the dominant paradigm in the cognitive neurosciences under the rubric of something called predictive processing, which was a sort of generalization of predictive coding to accommodate this inactive aspect of perception. So the free energy principle on one reading really is just a mathematical specification of this kind of active inference. The trick here is to cast things in a most general and generic way as possible, and by things I just mean the resolution of prediction errors. And the way that one does that is by appealing to the maths of Bayesian inference, and noting that exact Bayesian inference is not physically realizable. And you then have to turn to, well, how can you physically realize inference of this sort? And the solution was, in fact, on offer from in the 1950s from people like Richard Feynman in sort of Western physical sciences, but also hints at exactly the same solution in the early Russian literature in terms of algorithmic complexity and cohomolograph complexity. Those two perspectives converge upon exactly the same mathematical quantity, which is a variational free energy. So this is not a thermodynamic free energy. This is just a statistical way of measuring the thing that you want to optimize in any act of inference, whether it's your brain doing inference about its sensations, or whether, like Richard Feynman, you're trying to infer the probability distributions over the paths of small particles in quantum electrodynamics, whether you're trying to infer the message that was sent in cryptography, for example. All of these kinds of problems could be subsumed under one optimization process, which is the maximization of Bayesian model evidence. That's literally the likelihood of these data being generated by the model that you're currently considering. So that's in basistatistics known as Bayesian model evidence, and the variational free energy provides a tractable bound or approximation to that marginal likelihood or model evidence, which means that in its most general form, the problem of inference, and indeed the process of inference, if you don't want to consider it a problem, can be written down mathematically as any process that either maximizes marginal likelihood, model evidence, or if you're in machine learning, maximizes free energy as an evidence lower bound, also known as an ELBO, ELBO. There's a slight wrinkle here. In machine learning, they use the negative of free energy that Feynman used. So if I'm talking to physicists, you would want to minimize your free energy. If I'm talking to machine learning people, you want to maximize it. It doesn't matter from our point of view. The key thing is that you're just writing down the functional, the mathematical form of the quantity that underwrites the process of inference. That is a variational free energy. In optimizing, either minimizing or maximizing this, either by perception or through action, then you are effectively self-evidencing. And that's a term which I like from Jakob Hohen, that comes from philosophy, that if we understand ourselves as making sense of the world through a process of inference, then implicitly what we are saying is that we are all in the game of garnering sensory evidence for our models of that world. So we are literally self-evidencing, and you can just write that down as the process of maximizing Bayesian model evidence for your model entailed by your brain and your body, or you can write down as a physicist in terms of minimizing a variational free energy, and that's the free energy principle. And that's roughly where we stand at the moment. Although there are lots of unanswered questions construction.
You lay it out very, very nicely. It's very easy to follow there. I do have many follow-ups here about a few things. I'll try and keep them very general and kind of reframe some of what you said. So starting with Helmholtz, right? You were talking about how there's this inside out and outside in, right? That there's almost a kind of dichotomy in how we understand the world, right? Do we understand it from within ourselves, and then based on what, input, outputs, input, whatever way you want to describe it? Is it, and maybe that's just how it's fallen out, is it always kind of in these two camps or categories, or is there a third or fourth way? Is there another way where we could see a kind of mixture where it's not exclusively outputs from the environment or excuse me, inputs from the environment, and then we output. Is there some way in which we can understand that there's a third way or a fourth way or other ways in which these are combined, and where it isn't just input output, right? It's not just a kind of zeros and ones kind of thing. Is there another way in which there's an integration of them, or potentially some way of the phenomenology of how we're experiencing things? Is it always this kind of way in how it lays out? Because it seems throughout time, as you were saying with Helmholtz, there is this kind of dichotomy where people will kind of look at the dichotomy here, and then all the way to the machine learning stuff in the 90s, it kind of does this oscillating back and forth between where do we put the emphasis, where do we put it first. So I guess that's one component. The second piece here, when you were talking about, if I understand this, is the free energy principle. From what you're saying, sounds like it's the kind of quantitative and statistical ways of understanding the Bayesian model of the brain. And so they're kind of seen in tandem along with the active interference, which you explained. Connected with that, there's this emphasis on perception, especially with humans. So I wonder, with the predictive types of elements that you were discussing, where do we, this might be a little bit further out, and maybe some of this may be hard to know. All of this is very human. I wonder if we understand some of these things for non-human brains as well, such as with chimps or bonobos, or even other types of, it might not even be with primates. It could be, what do we understand about how potentially these workings of the brain could be for other brains that are non-human. So trying to look at a kind of evolutionary structure and model. And then finally, curious about if you have any thoughts about, you mentioned philosophy, and as you were saying that there was this kind of, in the 21st century now, not just an overemphasis on the brain, but how the brain and how it works is distributed through the body, and how the body is a necessary component, which automatically always makes me think of philosophy of Merleau-Ponty, who also thought a lot about perception, and in many ways had very technical ways of thinking about perception. He talked a lot about eyes, he talked a lot about sensations, and I wonder his estimation, how he was looking at the phenomenology of things, of how do we understand experiences through the body, that the body is a necessary or is a prerequisite of sorts, as a type of bridge for understanding our various perceptions. So those are my follow-ups. I don't want to throw it all at you at once, but any thoughts about any of that, I guess?
Right. You've just thrown all three massive issues at once.
Yes.
They're all wonderful issues. So we have to say at least something about each one of them.
Yes, please.
So in order then. So is there a third way that does not commit to an inside-out information extraction, or an inside-out construction versus a constructivist approach versus an outside-in extractionist approach? In a sense, that just is the Bayesian brain. That just is the free energy principle and active inference that is entailed by the free energy principle, because that is explicitly saying you have to have this two-way traffic. And this emerges in many different levels. So, for example, we've already talked about this sort of recurrent two-way traffic of message passing in the brain, from the sensory parts of the brain to the deeper hierarchically organized levels of the brain's generative model. This whole belief updating, this whole Bayesian mechanics depends upon this counter stream of top-down predictions and bottom-up prediction errors on a predictive coding architecture or view. So you've got this recurrence, you've got this circular causality for free, but even more generally, as you intimated in the third issue you brought to the table here, the very dependency of perception on action and action on perception. So put simply, I have to perceive and infer in order to plan what to do next. So action is predicated on my perceptual synthesis and making sense of the current state of my body and the world and what I want to query the world about. What kinds of questions, what kind of information do I want to get by deploying my sense organs. So that is almost self-evident, but in the same way that action depends upon perception, perception also depends upon action. What I see depends upon where I look, or how I place my skin in relation to an object that I'm trying to palpate. So there's this unbreakable circular causality and two-way street between action and perception. So I would submit that your quest for the third way has been delivered for you by the enactivist turn, by the enactivist application of predictive, to predictive coding, to the Bayesian brain hypothesis at the turn of the century. I think that is the third way. You can't tease these two things apart, really. So that should be comforting, and it should resolve any angst that we're missing.
Yes, it's very satisfying. Yes.
Good. Now, the second issue. What was the second issue?
The second one was about in non-human brains.
Oh, yes.
The evolutionary construct.
Yeah, the way that you asked that question makes me realize I've made a fundamental mistake here in terms of telling the story and unpacking the narrative of active inference in its sort of 21st century version. So most of what I've just talked about in terms of the mechanics of inference and optimal action could be applied to a thermostat or a virus. So I think I would actually put the question the other way around, and perhaps that's how you actually meant the question. I'm sure that we'll come to this later on. What is special about the human brain that has some unique and definitive properties that you would not find in a thermostat, that you would not find in a virus, you would not find in a mouse, you possibly wouldn't even find it in your most beloved pet, or some of our closer companions in say monkeys, on an evolutionary view. So I think that's that's the direction the question should be approached. It's less, what's special about mice. It's more, how do you make the move from mice to men under this kind of architecture? So most of the work that we do is at a much lower level. It's just trying to understand the fundamentals of active self-organization through the lens of sense making and inference that can be written down as a process that usually is actually emergent, an emergent property of any self-organizing system that preserves a distinction between itself and the environment, that doesn't decay, dissolve, dissipate, die. So, trying to explain how on earth does a virus survive, and what must it do in terms of this circular third way exchange between the inside and the outside to preserve its very boundaries and demarcate it from its external milieu, without worrying too much about what it is to be human. So we haven't got anywhere near a sort of Mark Soames-like set of questions yet. We are not talking about Bayesian beliefs as propositional beliefs that you and I might hold and be able to articulate. We are not talking about qualitative experience. We are just talking about the mechanics of belief updating on neuronal circuits, neural circuits, chemical circuits, electrochemical circuits that we see in every kind of biotic and possibly even non-biotic self-organization. So that's a deep question. And the answers to that question take you through a series of natural kinds of things that all are doing some inference of possibly a weak kind. And and can all be, if you like, described in terms of an ontology of generative models. If you remember before, we were talking about the underlying importance of a generative model in supplying the architecture under which you generate your hypothesis and your top-down predictions, and you use this is the thing that you are securing evidence for, which means that if there is a difference between mice and men, then there has to be something quintessentially different between the generative models that you and I employ to navigate actively our world and those that mice and flies use. And once one starts to think about it, one might ask, what is the difference between let's take viruses. Flies are a little bit too sophisticated. What's the difference between a virus and a mouse? And what's the difference between a mouse and me or you? And normally the story goes that it's all to do with the ability to plan. It may sound very, very simple, but once you've heard the argument, it is actually a very simple argument, but it's also quite a compelling argument and has a degree of explanatory scope, in the sense that the thing that distinguishes between a thermostat or a virus or some single-celled organism succumbing to nutrition graded through chemotaxis relative to something like a mouse that does stuff in anticipation of consequences is the ability of the mouse to plan. The mouse can think about and select those actions that have consequences. And that's absolutely profound when it comes to writing down or thinking about the generative model that mouse is using. It tells you immediately that the mouse has a model of the consequences of its action. If it has a model of the consequences of its action, given that the consequences occur after the action, then it also has a model of the future. So it now has a model that has a temporal depth. And this can be contrasted with a thermostat or a virus. The thermostat doesn't have a model of the future. It doesn't have an explicit hypothesis or question in its internal machinery of the kind, well, what would happen if I switched this heat-making device on or not? It just responds reflexly in the moment. But the mouse will have a much more elaborate model, sometimes described as a model with temporal depth, that frees you from the moment, but also crucially underwrites the ability to plan and thereby select from one plan or another plan, one course of action relative to another course of action, that endows that little agent with agency, because now it is selecting amongst a number of different courses of action that are entertained and can be supported by its generative model. So now together you've got this sort of move from a thermostat to a mouse that entails the notion of agency and temporal depth, simply because this generative model has the ability to model the consequences of action. So that's one move. Does that give you qualitative experience? Does that give you propositional beliefs? Do we have mouse philosophers who spend their time at conferences puzzling about why they see red, and does one mouse see the same red as another mouse? No, absolutely not. So we still haven't answered the question. What's the difference between a mouse and a man?
Just on the mouse thing, it sounds like what you're describing in the ability to have some planning sounds like there's at least a low level type of what we would call executive functioning, no? Where there's ability to plan, organize, sequence, right? Which we normally see in the prefrontal cortex for humans, but it seems like it's a very low level ability, whereas as we get to humans, there's a much deeper level of abstraction that we understand. Is this about right?
No, that's exactly and absolutely right. So all I am talking about here is exactly the prefrontal cortex and all the attendant executive machinery right down through supplementary motor area, premotor cortex, motor cortex down to the brainstem, and all the executive components that are responsible for executing the plans that are elaborated through selecting the right course of action in the prefrontal cortex. So that's exactly right, and that's what mice can do. They don't have quite as well developed a prefrontal cortex as we do, but they have the equivalent, the equivalent capacity to execute plans simply because they need to have that, because they have plans in their head. But having plans in their head is a remarkable capacity. A thermostat, I repeat, does not need to have a plan. It just responds as a reflex, as do many forms of lower life or biotic self-organization. So you also used hierarchically deeper levels of abstraction. I think that's the absolute key here. And then this question would be, well, what are you hierarchically abstracting? And I think most people would answer, well, you are now creating models of your executive process. So now a mouse has the ability to plan and to execute those plans by selecting the plans that are most plausible, in the sense that they will resolve surprise or prediction error or free energy in the future. We call that expected free energy, technically, which has some interesting aspects to it. So the mouse then has this ability. So what ability do we have because of our more evolved prefrontal cortices with these deeper levels of abstraction? Well, it could simply be to entertain the hypothesis that I am a person who is now selecting these plans, and it is me who is actually executing these plans. So, to a generative model that now entertains the hypothesis, the belief, the representation that it's me doing these things, it is me who is embodied, it is me who is the agent. So an agent doesn't need to know that it is an agent to actually plan and execute those plans, in the same way that a thermostat doesn't need to know it's a thermostat and that it's even acting. So I think that the levels of abstraction you're referring to here are exactly the abstraction and the plausible hypothesis that, in fact, I am an object, and indeed I am the subject of my own observations and actions. And having that hypothesis as part of the generative model now has to be explained. And how can it be explained? How could it be that I now have a better generative model or explanation of my sensorium that has been actively constructed simply by having this notion that I am a person? And I think there are quite simple answers to that, because of course it's not just I am a person. I'm a person in this belief state or that belief state or that emotional state, or this intentional proposition state. And once I recognize myself to be in that state, and implicitly now I have a degree of qualitative experience of my inference lower in the hierarchy, then I can now bring to bear and contextualize all my message passing and inference conditional upon my now recognized state. So, for example, if I know that I am anxious or I am embarrassed, I know that there will be certain kinds of information to which I will be paying attention. There will be certain sort of autonomic actions that I would normally be engaging in this context of being embarrassed or being frightened, such as cardio acceleration or paying particular attention to auditory and visual streams, for example. So there is an easy to argue benefit for having these higher levels of more deeply abstracted representations and explanations for the active inference and all the message passing that's going on underneath. And I think, if you go right to the top of the hierarchy, to the very highest form of human life, which would be a philosopher, what you find there are representations and hypotheses that just are qualia and qualitative experience. So, this is touching on now something which David Chalmers has popularized as the meta problem or the metahard problem. You know, is why do we puzzle about our qualitative experiences? You know, mice don't do that. Well, so what special aspects of our generative models can explain the very fact that we can entertain notions like being a zombie, for example, or thought experiments like brain in a vat? The very fact that we can entertain these counterfactual, outlandish hypotheses about self is the gift, if you like, of having these deeply abstracted representations of how we engage with the world. You know, first of all, just having a representation of me or selfhood, and then, you know, me as an actively inferring agent that must, in some sense, have some internal action over the way in which I secure the evidence and test my hypotheses. I'm trying to work here to something which I think Mark Soames may have talked about, which is, you know, what underwrites the feeling part, the qualitative experience that the philosophers talk about in terms of qualia. You know, the essence that we think we can entertain and have discourse about that perhaps a mouse might not be able to talk about. It may have, but it wouldn't be able to recognize it or talk about it. It's just not there. It just can't see that kind of thing in the same sense that a blind person can't see color. It may well be that a mouse just does not have these hierarchical levels of abstraction, so it's just not perceivable in the sense of Helmholtz. You know, you have to have it in mind before you can sense it. The argument, the answer that somebody like Mark Soames, I think a lot of people would bring to the table here, is the notion of confidence or precision, or a representation of uncertainty in one's beliefs and getting that right. And that basically entails a kind of mental action. So now we're talking about action, not on the outside, not autonomic actions like secreting something or cardio acceleration. And we're not talking about motor actions, motor reflexes, moving my limbs around with my striated muscles. We're talking about a covert internalized action where very, very high levels of a hierarchy, or very deep levels perhaps, you know, at the center of the brain, from Mark Soames' perspective, have an influence on the belief updating that underwrites the action selection. And that influence is really a statement that we're able to represent our own beliefs. We have beliefs about beliefs. The particular example here is we have certain beliefs about our beliefs that pertain to the uncertainty. So if you have in mind the simple mathematical description of a belief as a probability distribution, so when people talk about Bayesian beliefs, I repeat, they're not talking about sort of ideological or theological commitments. Sure. Or, you know, they're just talking about the brain as a sentient artifact that is somehow encoding a probability distribution. And invariably, these kinds of beliefs, these Bayesian beliefs or conditional probability distributions, have two cardinal aspects. They have a location, so that the most likely thing, I believe, or the Bayesian belief entails, is designated by the peak of the probability distribution. But there's another shape parameter, another aspect of this probability density or distribution, which is its spread or dispersion. And that's usually understood in terms of uncertainty. So a very broad distribution means that all of these things could be in play, whereas a very sharp, very precise distribution means that I'm pretty confident that it's just underneath this very sharp distribution. So that precision is a really important attribute of the belief. And if parts of the brain now have beliefs about beliefs, they are now predicting precision.
Mm.
predicting predictability.
Mm.
And that may well be the thing that calls for covert mental action and the need for recognizing that I'm in this belief state or this state of uncertainty or that state of uncertainty, and then I can now deploy the appropriate beliefs about beliefs or predictions of predictability or predictions of precision.
Mm-hmm. Yeah, it's interesting on that last point, because what you're sounding like you're describing is this type of metacognition that's interested in our own epistemology and also our ontology as well, right? That we're very concerned about our beliefs and how we have these beliefs about them, or even things about our own existence or things about us, who we are as beings. One other point I wanted to make about the abstraction piece is that I totally agree, obviously, but I think even more miraculous, if you will, or more wonderful is the fact that for humans, not only can we have these levels of abstraction, but I always think of this example of, like, I can know that I'm thinking about a concept, or I can know that someone else is potentially thinking about a concept, right? There's this way of abstracting with the other. But even further, if you take works of fiction, let's say I'm reading a novel and the central character is thinking about a thought he had in a dream that he had. And I'm the one reading that thought that someone wrote. You have like 6 layers of abstraction there, right? There's this very big, wide lens of things, which is incredible. It's incredible. Our mind doesn't, fold up, because of how complicated or complex that is. And I don't know if other animals on the planet can, read novels and get the whole construct, or if people watch a movie, right, and they can see or observe all of these things. So it's very interesting about the abstraction, and I liked how you linked to it the various components of executive functioning for detailing that. We've talked a lot about the Bayesian brain, and we've mentioned many components of it. Maybe we can give for listeners the kind of overview of the Bayesian brain, and then that will kind of dovetail into the free energy principle, and I'll give you a lot of runway for that. You can talk all about that. So you correct me here if I'm wrong. My limited understanding of the Bayesian brain is that the brain is essentially equipped with an internal model of the environment, and that gives us a plan for how do we create sensory observations from hidden states, right? That's one way of saying it. And that there are these hidden variables that are from a prior distribution. You could say, maybe, I don't know, if you want to use a Freudian term, the unconscious. We can come to Freud at some point. And then also that these sensory observations have a distribution conditional on the hidden state. So then you have these priors and you have a likelihood combined to infer the hidden state given the observations. So I think the clarifying point here is that these aren't specific claims about priors and likelihoods for an individual, but more so on the consistency of them. That's my very limited scope of the Bayesian brain. So maybe kind of branch off of that and just kind of give us the full overview of what we mean by the Bayesian brain, priors, likelihood, hidden states, and then we can jump into the free energy principle.
Right. Well, I mean, that description was spot on in itself. So all I need to do is to connect what you've just described to what we're talking about. So I think that we basically have done the Bayesian brain, and we've done the finest and most delicate aspects of the Bayesian brain under a hierarchical generative model. When you started talking about the 6 degrees of hierarchical embedding, and I'm glad you used the word metacognition. So that's what I was trying to imply when I was talking about beliefs about beliefs. This is exactly it, and it is this hierarchical recursive embedding, which is quite remarkable. I can't remember whether you use the word fall down or unfold, but certainly, at about 6 degrees of recursion, my brain gives up, and I think at that point, that may be the explanation for the metahard problem that even philosophers can't quite handle that, and that residual puzzlement, inspires us to try and get to the 7th or the 8th. But it is exactly that sort of beliefs about beliefs about beliefs. The other key thing you just brought to the table before just unpacking the Bayesian brain in the language and the setting that we've already established, you brought another really key thing to the table, which is inference about others. And I was tempted to say, well, perhaps that's one aspect of the third way that we haven't talked about, we haven't spoken about, and perhaps we should have spoken about, because everything that we've spoken about thus far would work for a single agent in a universe that did not have anything else like it in that universe. It's just making sense of a universe. But of course, most of the interesting questions in terms of self-understanding are in light of or contextualized by the need to understand others. So we're now moving from the Bayesian brain and beyond that to the embodied Bayesian brain, which is the third issue that we still yet to talk about. But now to multiple Bayesian brains in an ensemble, all trying to infer each other. And that brings some really interesting questions to the table about self-understanding in relation to others' understanding. And there could be an argument that the need for selfhood, or an explicit ability to recognize I am a self, and to have at least a minimal selfhood, is just a product of being required to disambiguate the causes of my sensations in terms of, did I cause that or did you cause that? Or perhaps more practically and more relevant would be during very early neonatal experience. Did I cause that or did mother cause that? So mother being the key other. And just being able to, first of all, recognize that mother is actually an object out there that is distinct from me is a great move to be able to do, and something that takes sort of a long time for a neonate to, and not every neonate recognizes that and can learn the appropriate generative models that explains interactions or our interactions with mum in terms of mum being a creature. And of course, once you realize that mum is a creature or an object out there, then the natural hypothesis might be to entail, well, perhaps I am a creature. And why would you need to do that? Well, you need to do that to disambiguate. Did I cause that or did mum cause that? So that elemental theory of mind, that ability to distinguish between the causes of sensations in terms of self versus other, may be unique to creatures that have a universe or an environment that is populated by creatures like them, such as you and me. So I think this is a really key aspect of this sort of self-evidencing. Self-evidencing, yes, but it's in the context of a whole world comprised of things which are just like me. So I have to now be very skilled at differentiating me from you. And in so doing, of course, that pressure is only evinced if you are sufficiently similar to me and cause the same kinds of sounds and repetitive touches and sensations that I could cause. I don't need to do that, given that you are physically very similar to me. But if you're that similar to me, I can now use my generative models, my explanations of the world to explain, which I would normally use to explain my autonomic dispositions and my bodily sensations or my movements. I can now use those prior beliefs, selections of the plans that we were talking about, our intentions, to explain your intentions, or more specifically, to explain your behavior, your facial configuration, your micro expressions, your physical stance, in terms of your intentions, which would be the intentions I would have to have in order to witness and to manifest the same kind of observable behaviors. So I think that that's a really important thing you brought to the table when in terms of selfhood and self-evidencing, or being particularly acute and important in the context of a world that has a culture that is born of the fact that we populate that world with lots of conspecifics, and we have we have a shared eco niche in which to do that. I just wanted to put that on the table because it's a really important sort of thing when it comes to sort of interpersonal exchange and
absolutely.
But back to the Bayesian brain. Well, you just summarized it. I mean, I don't. You've done all the heavy lifting there. I think it's probably best just to say out loud at this point, there is nothing that the Bayesian brain brings to the table we haven't already spoken about. It's just one way of articulating the kind of sense making where we have, say, prediction errors ascending the hierarchy from the sensory cortex, the sensory parts of our brain, and updating representations that would be, in a Bayesian sense, regarded as posterior beliefs. So what I'm going to do now is just tell the Bayesian brain story from the point of view of somebody who likes to talk about predictive coding. So we've already established predictive coding. Predictive coding, I should just add, if I was talking to an engineer, I wouldn't use the word predictive coding. I would use the phrase Bayesian filtering. The simplest instance of a Bayesian filter is something called a Kalman filter, which is used widely in state estimation. So predictive coding just is Kalman filtering of an extended and nonlinear form, sometimes known as an extended Kalman-Bucy filter of a hierarchical sort. So these things are all the same, but different people like to use different language. So how would you understand Bayesian inference from the point of view of predictive coding? Well, as you say, Bayesian inference is just the process of belief updating. How would you articulate that from the Bayesian brain hypothesis? Well, that update is just an update to your Bayesian beliefs, your conditional probability distributions, prior to seeing some data, to some beliefs after or a posteriori. So you're just updating your prior belief to your posterior belief. You're literally changing your mind. You're just moving through changing neural activity or weights or connection strengths in your brain. You're changing the implicit or encoded Bayesian belief from a prior belief before you saw the data to a posterior belief after you saw the data. And that movement from one belief to another belief, literally changing your mind, is the updating that is driven by the prediction errors. So the next question then would be, well, what is the nature of that updating? As we, if you like, mix together the prior belief and the information afforded by the likelihood of these data to produce the posterior belief. So that's just to explain to the listeners why there were three kinds of beliefs. There's a likelihood distribution, a prior belief, and a posterior belief. And really the likelihood, if you mix together the prior belief and the likelihood, then you get the posterior out. So the likelihood stands in for the pressure or the forces applied to changing your mind that drive a change in mind or the belief updating that are afforded by the data. And this is, I think, a useful view because it allows us to come back to this notion of precision. It's difficult to do without a whiteboard or a blackboard. But let's have a go, because this is, I think, an intuitive and really important observation, which brings us back to this mental action and the notion of predictions of precision. So if I had a very, very vague, imprecise prior belief, and I had some very definitive, very precise sensory evidence that could be of an elemental sort, like a particular pattern of visual impressions in a well-lit room, or it could indeed at a more abstract level be some definitive information from Wikipedia. But if it's very precise, then that precise likelihood will have a very sharp narrow distribution and will pull the soft, flat prior distribution much closer to the likelihood, so that my posterior now is dominated by the shape and the form of the likelihood. So I've induced a much greater degree of belief updating. I've changed my mind considerably more than I would have done, simply because I ascribed a greater precision to these data, so it had a much more precise likelihood. Conversely, if I have a very, very precise prior belief that is based upon lots and lots of experience, then it's going to be much less sensitive to any likelihood or any belief updating. So my posterior is going to be, if you like, tethered to my prior belief. As I change my mind and I move from my prior to my posterior, when seeing the evidence, doing my Bayesian belief updating according to Bayes' rule, I will move a much smaller distance from the prior belief. So the precision afforded both the prior belief and the likelihood, in fact, it's the balance, the ratio of the two, becomes a really important quantity in any Bayesian brain or any Bayesian scheme. In engineering, this would be the Kalman gain, for example. It's how much gain do I afford prediction errors in updating my estimate of the hidden state that I can't see. So that places this notion of the encoding of and the predictions of and the optimization of precision center stage in the Bayesian brain. You see this in many, many guises. You can see it in the context of multisensory integration. So how much precision do I afford the visual evidence relative to the auditory sensory data? If I'm in a very, very well-lit room, I might ascribe much more precision to the visual information, and that will dominate over my belief updating, and my beliefs will be driven by what I see, not what I hear. But if I reduce the precision of that visual information, those visual prediction errors, and switch off the lights, so now in a dark room, that now becomes very imprecise, and now the most precise influences of my posterior beliefs are going to be the auditory modalities. I'm going to listen very, very carefully in a dark room. I'm going to pay attention to the auditory sensations, not the visual sensations. So that I've used the word attention deliberately because this, from a psychological perspective, what we're talking about is deploying the precision in the right way, in the right context, just is attention. It's what we attend to. And that attention can operate at any level in the hierarchy. It can be sort of attention-grabbing stuff in a particular quadrant of my visual field, some flutter which is unexplained, that can now draw attention at a very low level in the hierarchy. Or I could be deploying attention at a very, very high level of the hierarchy, in terms of who I'm going to listen to next, or who I'm going to place some epistemic trust in, what news channel am I going to select next. So this process of selecting by assigning or affording precision to this or that is exactly this mental action that we were talking about before. It's just deploying attention in the right kind of way. And that attention, mediated through the precision of either prior or likelihood beliefs, has a profound effect on the degree to which I change my mind. So it's a really important aspect of this belief updating.
At the neuronal level, the predictive coding theory, it has two classes of neurons, which is the prediction neurons and the prediction error neurons. You've mentioned this already, but I'm just asking at the neuronal level, this is what's happening within the neurons. There you have these two classes of neurons that are essentially weeding out, is this a prediction, and how are we parsing out some of the prediction error? This is what's happening at the neuronal level?
No, absolutely. And it's nice you sort of ask that question, because that allows us to connect this predictions of precision or predictability that underwrites optimal belief updating and Bayesian inference to pharmacology and to the kinds of neurochemicals that may be aberrant, say, in things like schizophrenia or indeed depression or autism. And ASD, and also implicate all the drugs that have a psychoactive aspect, from psychedelics through to the kinds of drugs that people prescribe say, psychotic depression. So yeah, let's just unpack that. So now we've done the Bayes rule and the Bayesian brain with in our mind's eye, three probability distributions all being mixed together in the right kind of way according to their dispersion or their width. But now let's say, well, how would that be implemented in a Bayesian brain? Well, the implementation just is a Kalman filter. It's just a predictive coding. What would that look like? Well, on one view, as you say, it would just involve two kinds of populations, one encoding the prediction error and the other encoding the expectations or the hypotheses, the representations that are generating the predictions that are sent down to form the prediction error. So this again speaks to this recurrent message passing between the prediction neurons, sometimes ascribed to the cells that live at a slightly greater depth on the surface of the brain, the cortical layers, relative or distinct from populations encoding the prediction error, sometimes ascribed as superficial pyramidal cells, simply because they live very much closer to the surface of the brain. So you've got this sort of reciprocal exchange of messages where you can think of the deep pyramidal cells or the deeper cells as encoding the position of the posterior. So let's say some information comes in from the sensory epithelia. There is a prior belief encoded by the activity of a deep population of deep cells, and they provide a prediction that is now not an apt explanation for this new information that's coming in. There is a prediction error. The prediction error is reported by the superficial pyramidal cells. That is then sent forward to change the deep pyramidal cells at the next level. This is just the belief updating. So now the deep pyramidal cells that were previously encoding the prior expectation here is just used as a word to mean the mathematical average or the most likely value of our belief. Then the prediction errors can now be seen as doing this changing of mind, doing the belief updating, just by driving the activity of the deep pyramidal cells in proportion to the precision of the prediction error. So if you ascribe a lot of newsworthiness, a lot of precision to these kinds of prediction errors from this modality in this point in time, then what you are doing is effectively boosting them, increasing their potency, their gain or their drive, so that they cause a bigger belief updating or shift or change of your mind, simply because they're driving the deep pyramidal cells towards the likelihood to a greater extent and away from the prior than had the prediction errors had been assigned a much lower precision. So what would precision look like from a neurophysiologist or a pharmacologist perspective? Well, it's just the excitability of these superficial pyramidal cells encoding prediction errors. So that tells you immediately anything that changes the excitability or the sensitivity of populations encoding prediction errors under a predictive coding scheme is going to be the physical or biophysical realization of this precision, which then you ask, well, what kinds of things could change the excitability or the postsynaptic gain, sometimes used in neurophysiology? Well, in the brain, there are certain brain chemicals or neurotransmitters whose role is just to modulate the gain of these kinds of cells. And what you then ask is, well, what kinds of neurotransmitters? Well, ones which many people have heard of. So classic neurotransmitters of a neuromodulatory sort would be things like adrenaline, oxytocin, dopamine. I've slipped in oxytocin there for a particular reason, but dopamine will probably be the sort of the poster child of this kind of neurotransmitter. But there are others, acetylcholine or cholinergic neurotransmission, serotonergic neurotransmission of the kind that's influenced by, say, psychedelics, psilocybin, for example. So you can see immediately, if you've heard of any of these drugs, you will know that they can have a profound effect on the way you feel or the way that you update your beliefs or respond to changes in sensory contingencies or changes in life circumstances. And of course, it is these neurotransmitter systems that are responsible for setting the game and computationally thereby the precision or the ability of prediction errors to drive belief updating higher in the hierarchy that are used in a therapeutic and also recreational setting.
Yeah, it's really important how you're connecting everything here with not only the two classes of neurons, but then also bringing in the neurotransmitters and how they're also functioning here as well. I want to give you a lot of runway here. Many of this will start to tie in together, so hopefully listeners will be able to see that. But give me your detailed explanation and analysis and exploration of the free energy principle. Just lay it all out for us. Just describe what it is, how it works, how it functions, and then how it connects with, many of the things we've already discussed. I'm sure it will come up with active interference, predictive coding theory, and Bayesian brain model. So just tell us your free energy principle, what it is and how it works, and you can be as detailed as you would like.
Right. I guess I don't want to exhaust you.
No, it's great. It's funny because I feel like at this point we've done all the warm up, so now we can get to the entree. We get to the main course here. So tell us about the free energy principle from yourself.
Right. Yeah, I have to confess, that warm up was probably a more substantive aperitif than you might imagine. I think we've done 90% of the heavy lifting here. Excuse me. In the sense that the free energy principle provides a first principle account of the mechanics that we have been talking about. So I'll try and explain what the free energy principle is in a second, but perhaps just preface that by noting that it plays the same role as Hamilton's principle of least action, and you could even argue the theories that undergird natural selection evolution. So in and of themselves, they don't do much heavy lifting of an explanatory sort. For example, knowing natural selection is a principle by which you and I are here. It doesn't tell me anything about why you've got eyes or a nice little beard or you've got your particular accent. It tells me nothing about that.
Right.
It just tells me there is a mechanism, a principle account as to how these things could have emerged. So the free energy principle is a little bit like that. I'll give you another analogy. Hamilton's principle of least action, it's a generic, I would say, foundational principle that underwrites all known physics, arguably. And yet it doesn't tell me how on earth I'm going to throw this ball. I mean, if you tell me all the processes, all the mechanics and the initial conditions of a particular instance of ball throwing, I can certainly compute the trajectory of the ball. But in and of itself, it doesn't. It just tells you the principles that underwrite the actual process of ball throwing. I'd actually have to become an expert in ball throwing to actually realize and apply the method of or the principle of least action. And I use the principle of least action because the free energy principle is just a principle of least action. So it's a principle that could be read as a method that could be applied to a particular instance or circumstance of self-organization or active inference. But you're going to have to write down all the actual aspects of that circumstance in order to make the principle do any work. And in a sense, what we've been talking about in terms of various perspectives afforded by predictive coding, the Bayesian brain, embodiment, all of these are really process theories, accounts of a realization of the free energy principle. So I just put it setting the scene, and to qualify my statement that the starter was actually the main meal, because all the hard work and the heavy lifting is really in testing these different process theories and understanding how the free energy principle operates in this particular context with this particular creature, this particular institution, this particular aspect of self-organization. So having said that, then what is the free energy principle? Well, it's sort of transmuted to a certain extent depending upon how the story is told. Nowadays, one would really tell the story from the point of view of a physicist trying to understand self-organization under a particular constraint, and that constraint is that you are trying to understand the dynamics and the physics and the principles of least action that would apply to something. Now, that may sound really trivial, but it's in fact quite an important starting point. If you want to talk about something, then you have to say, well, what defines a thing? What separates the thing from nothing or from something else? And immediately you get into the game of defining how you'd separate the states of a thing from something else, the states that were external, say, to that thing. And this leads you into the world of Markov blankets and conditional independences, statistical devices that enable you to say that there is some independence or disentangleability between the states of this thing and the states of everything else. And basically what happens is when you apply Hamilton's principle of least action to the dynamics of joint systems that possess a Markov blanket that separates the thing, we usually call it a particle, from something else, then what emerges is basically a Bayesian brain, or a Bayesian mechanics that could be applied to a brain, but also to a thermostat or to a virus, which is why I was saying before, the way that we deal with things is in a much, we usually start with very, very simple systems. So to cut a long story short, what you are doing is engaging the same sort of questions and formalisms that people in physics would engage if they're trying to understand non-equilibrium steady state dynamics. And why is that different from 20th century physics? Well, because most of 20th century physics was all about equilibrium systems. It's all about sort of idealized gases. It's all about second laws that apply to closed systems. And by closed systems, what I mean is that you've got this sort of system of exchangeable particles that's in a heat bath or in a heat reservoir. And I use the word heat bath here because the question that somebody interested in open systems would be asking, where did the heat bath come from? And what's outside the heat bath? And how on earth did the heat bath maintain itself? So you're now starting to ask questions that people in the life sciences have been asking, people like Varela in terms of autopoiesis. How on earth does the boundary, from my perspective, the Markov blanket, the heat bath that contains the idealized internal states of inquiry that define the particle in question, or the system in question, how on earth is that maintained? And even more simply, its very existence and persistence, what does that imply? And if one just follows through the maths that you would normally apply to an uncontained states of a system, to a contained set of states that are contained within a Markov blanket that comprises sensory and active states, then what you end up with is a functional expression or functional form for the dynamics that is formally exactly the same that you would find in the other kinds of mechanics. So, you can think of the free energy principle as just basically introducing a different kind of mechanics that is a complement to, on the one hand, classical mechanics that would apply to heavenly bodies and massive bodies where there were very few random fluctuations in play because they're so big or cold. On the one hand, the second kind of mechanics that you'll get in the absence of a Markov blanket would be statistical mechanics, thermodynamics, fluctuation theorems that apply to lots of very hot, very small things that don't have conservative dynamics, where the random fluctuations dominate over the classical conservative dynamics of Newtonian mechanics. You can even apply it to quantum mechanics. And the move here is just to work with the complex root of probability distributions, Bayesian beliefs, but the wave function squared now becomes a Bayesian belief. But you don't have any Bayesianness in either in any of the classical mechanics or the quantum mechanics or the statistical or stochastic mechanics. And that's because none of these mechanics have a separation between the inside and the outside. And it comes back to something you mentioned earlier on, which is the notion of hidden states. You remember, and I should have picked up on that when you were framing Bayesian thinking. So the whole point of Bayesian thinking is there has to be an inside and an outside. So there has to be observable consequences of causes that are unobservable. So that, before you can even talk about inference, there has to be something about which you are making an inference. And there has to be some data, some observable consequences of these hidden states or hidden causes that now you plug into your Bayes rule, and we can then go back to the story about moving a posterior from a prior, given the likelihood of your observable sensory data. But just standing back from that construct means you now have to have a physics that makes a distinction between stuff on the inside, the internal states of a system, and stuff that is hidden, states that are hidden that will now support a Bayesian inference. And of course, this is exactly what is supplied by the Markov blanket. So the Markov blanket is a set of states that intervenes between the inside and the outside, that literally surrounds, forms a blanket, a shield, a veil of a statistical sort that encompasses, enshrouds the internal states. So now what plays out on the surface, on the blanket states, are now the sensory data, the observations, the sensory evidence that are reporting the influence of the external states on the outside that are hidden from the internal states because they are behind the Markov blanket. So you have to have a Markov blanket that separates the inside from the outside before you can have a Bayesian mechanics. But once you commit to and follow through the maths that would apply to a partition of a universe into internal, external, and the intervening blanket states that, I repeat, can themselves be divided into active and sensory states, then you just get the free energy principle. And all that says is it looks as if any system that is equipped with a Markov blanket and has to be in order to define the thing in question will appear to infer, in virtue of the dynamics of its internal states, the external states. To put that more concretely, there will be an interpretation of the physical internal states as encoding the parameters of beliefs, Bayesian beliefs about external states. And by parameters, we're just talking about these location parameters and shape parameters that parameterize or describe any belief. So that's quite remarkable because it gives you a very different kind of take on information. Because normally when people talk about sort of information theoretic treatments or probabilistic treatments in self-organization, non-equilibrium, steady state sort of treatments that allow for this openness or exchange between the inside and the outside through the Markov blanket. They're talking about the information inherent in any particular state. How surprising would it be to see this gas in this ensemble in this configuration? What we're talking about here is something much more subtle, and it's a kind of information that is much closer to a folk psychological or a lay notion of information. It's information about things that can't be seen. So the internal states now hold Bayesian beliefs about hidden external states that are hidden from them because of the Markov blanket. That defines their existence. So there's an existential imperative here, or one can read this existential imperative as this inference process, which brings us back to self-evidencing. That just to exist as a thing means that you have a Markov blanket, which means that there are hidden states, which means that if you exist and persist, you must be in some kind of technically generalized synchrony with the external states. That means that I can read off your internal states and infer, and indeed you can as the thing, the configuration of external states. And that this process in a dynamical setting now becomes a process of belief updating, becomes an inference process that can be described technically as minimizing a path integral of a in physics called an action, which is a time times energy construct. Hence Hamilton's principle of least action. In our instance, the action is the marginal likelihood of the sensory states, part of the Markov blanket, which is approximated by, or may in some instances be identical to, the free energy. So hence the free energy principle is just a principle of least action. It's saying that the internal states of anything that exists will have a description in terms of minimizing technically a functional of beliefs about external states. So that was a very brief, ironic.
So let me try and summarize here if I can get this. So what you're saying is that so all biological self-organizing systems, they are ergodic, they have the Markov blanket, they exhibit active inference, and they are for self-preservation, or to put it another way, all of the quantities in a self-organizing system that can change will change to minimize free energy. Do I have this right?
Yep.
Okay. So I want to go to this idea of hidden states, right? So obviously you talked about equilibrium, and I think maybe I would term it in my world, it's something around homeostasis, right? You know, people in psychology or people that do physiology, they like to talk about homeostasis. So maybe you can chat a little bit more about the role of homeostasis or equilibrium in preferred versus expected various physical states. I do want to introduce a little bit, because I know we've mentioned him a few times. You know, Mark Solms, I know you guys have worked together. I've talked to him. He's fabulous. So he has a psychoanalytic angle here, which I'm very fond of as well, about the impact of the Freudian model of drive energy. So maybe this is I'm adding something here. So maybe you want to talk about homeostasis. But my question about Freud is, how does his conception of drives or drive energy, how is that consistent with your free energy principle?
Right. So two really easy questions there. Right. So you want to go from Bernard to Freud. But that was, that was, I think, a clever move to introduce the notion of homeostasis. So what we're talking about here is just a generalized homeostasis. So, you can regard this non-equilibrium steady state. You use the word ergodic, which was interesting. We try not to use that word because that brings all sorts of baggage. What we're implying in terms of a non-equilibrium steady state is over a limited period of time, realizing that, of course, at a slower time scale, things will evolve. So that we don't imply that the system ever attains a steady state. It's just that it has a steady state solution to its dynamics, but that solution may disappear after a short period of time. But within a particular time scale, what we are talking about is the fact that it has maintained its Markov blanket, which means that it must have established some kind of synchrony or balance between the inside and the outside that we can now articulate as a principle of least action or a principle of least free energy or maximum model evidence. And then the question is, well, is this consistent with other theories and other accounts of self-organization or global function of a system? And the answer is yes, absolutely. So, homeostasis is one of my favorite accounts, but there are other accounts. You can also say, well, this fundamental objective function that appears to be minimized. Remember, this is a principle of least action. It looks as though it looks as if the system is trying to minimize something. Mm-hmm. So that could be a cost function, which could be a negative reward function or a utility function. So you can now spin off all of reinforcement learning and economics in terms of utility theory as one expression with a particular commitment to understanding the mechanics and the rhetoric of that field, either in the economics or psychology sciences. But it's just really an expression of that there is something to be optimized, or it looks as if the system is optimizing something because it conforms to this principle of least action, where action is the negative log evidence or the free energy. So all of reinforcement learning and utility theory is just a statement. I think I can describe the behavior of this system as an optimization process. All I need to do is to identify the function that's been optimized. And of course, from our perspective, that's going to be, or minimized in our context, that will be a free energy, or its converse, the marginal likelihood, the evidence of my model of the world. So you can rewrite all of reinforcement learning and utility theory as basically an expression of, or an optimization process of self-evidencing, where you now start to interpret the prior beliefs as, or the logarithm of the prior beliefs as a reward function or preferences. So just because I am sitting in this configuration with my Markov blanket means that if I now interpret my behavior in terms of Bayesian mechanics, I necessarily now have to understand it or write it down in terms of a prior belief and a posterior belief and the updating. And it turns out that that prior belief just is the distribution of the steady state solution that we were talking about previously, which means that just existing is a statement of your preferred states of being. And you can articulate that mathematically in many different ways. So, for example, in the theory of random dynamical systems, the set to which you will always return will be called a pullback attractor or a global random dynamical attractor. These are just the states to which I'm attracted. These are my preferred states. And of course, that's what's been optimized from the point of view of reinforcement learning or utility theory. You can move then to the observation that the negative of these utility functions or value functions is surprise. That's also known as self-information information theory. It's just the prediction error we were talking about before. We're trying to minimize that. And then from that, you can read off all sorts of information theoretic treatments of optimal behavior, such as maximum mutual information theory, Informax theory. You could even go as far to a certain extent as integrated information theory if you wanted to. But information theoretic accounts that posit some metric, some functional information theory measure that is extremized. Of course, the free energy principle is just one of these. It says that the information theoretic measure is just the free energy, which is a bound on the negative log model evidence or marginal likelihood. But then you come to your set of examples, which would be more from the point of view of theories of self-organization, either of a sort of physical sort, like cybernetics, and then you get into things like the good regulator theorem and or synergetics, which are entirely consistent with this sort of optimization, the Hamiltonian principle of least action. But if you're a physiologist, all you're saying is just homeostasis. So this is just a generalized homeostasis. It's trying to place bounds upon, or it looks as if we're in minimizing your prediction errors. If you now think of a particular kind of prediction error as the prediction error between any autonomic physiological variable and your a priori set point or belief about what it should be, in minimizing the prediction error, you are doing homeostasis. So minimizing that surprise in the particular setting of the surprise being about physiological states just is homeostasis. And if you just generalize that, all you're doing when you're describing a particle that keeps its states within particular bounds within its Markov blanket, it necessarily has to resist random fluctuations and gather itself up to evince a generalized homeostasis. And then the final interpretation, of course, is just in terms of self-evidencing and the Bayesian brain hypothesis. But these are just different perspectives on the same underlying dynamic. So having established the primacy of homeostasis in its full and generalized sense, we just have to put Freud into the story, which is not that difficult, actually. And I say that because I should acknowledge that Mark Soames is the world expert on Freud, and I don't know if he spoke about his books on Freud and all the translations. So my understanding is childish and unscholarly, to say the least. But from what I understand, having spoken to people like Mark, many of Freud's foundational ideas were coincident or shortly post-dated much of the work of Helmholtz. So when what one might easily imagine that Freud, thinking about sort of his energy constructs in terms of a Freudian construct, he probably had in mind the same kind of thing that Helmholtz had in mind. And I haven't seen anything written, or I haven't read about this, but certainly from secondary and tertiary sources, Helmholtz did have a notion of a neuronal free energy, or a neuronal energy, that was the thing that could be optimized or minimized in order to explain unconscious inference. He never really articulated or found it, but he certainly had the quest in mind that I fondly would now submit would be the variational free energy. It fills everything that he wanted and is entirely consistent with his more formal formulations of perception and also much of physics. So my guess is that basically Freud was taking that notion of an optimization in terms of an energy function as it was articulated and conceived of at the time that these the inception of these ideas, that you're bringing Kantian philosophy into physics, but without the machinery afforded by Richard Feynman to deal with it in a simple and graceful way in terms of mathematical equations, and without, of course, the high performance computing that machine learning subsequently enjoyed and was able to sort of demonstrate proof of principle that this is the way to formulate the problem. So Freud probably got as far as he could in the absence of Feynman-esque maths and mathematical formulations and big computers, but pursuing the same kinds of ideas. So it's of no surprise to me when Mark tells me that there is a fundamental consilience between Freudian formulations and those that you would find that inherit from Feynman and all the other contributors to these to this formulation of sense making. So I would imagine that Freud gets into the game quite gracefully. The particular point I think that Mark Soames would emphasize here, though, brings us back to this this metacognition and beliefs about beliefs, and in particular the ability of certain hierarchically abstracted, sophisticated particles like you and me to actually physically encode and manipulate and do their Bayesian belief updating on beliefs about beliefs, and specifically the precision, the uncertainty, to know our own uncertainty, to know our own minds. And the deployment of that in terms of this overarching homeostasis, this extremization of or minimization of prediction error or free energy, or maximization of marginal likelihood or model evidence, underwrites that kind of mental action and may, on Mark's view at least, be the essential quality of any feeling or any sentience. So he has a lovely phrase called felt uncertainty. In the same way that we visually palpate the visual scene with our eyes, what he's suggesting, well, the way that I interpret his poetry, he may be very cross if he hears this, but the way I interpret it is that you can palpate your own uncertainty, you can feel your own precision, and furthermore, you know and have prior beliefs about the way that uncertainty should be deployed or changed, and you update your beliefs about that precision. And the mechanisms that do that may well be those that are at the heart of the feelings that underwrite qualitative experience of the kind that Mark would ascribe to consciousness, to that felt uncertainty.
Yeah, it's interesting with Freud, because obviously a lot of it in terms of the drives was this. I'll say it was in an interesting way. I mean, the way he framed it was, in terms of the psychological hierarchy that he was trying to give as a model, was this element of tension reduction rooted in our biological and evolutionary nature. If you were to make a comparative analysis here, you would say that was probably a passive approach, right? Because it's always something is happening. How do we resist? How do we get rid of the tension reduction? Is it in a way a kind of passive way, as opposed to maybe say the philosophy of Friedrich Nietzsche, who had a more active way of trying to understand energy and drives and power and things of that nature. Okay, so some of the further questions I want to ask you are since we've done a very nice, or you've done a very nice job of explaining the free energy principle, I want to ask about how it applies, and then a little bit of some criticism. So I guess the one connection here is about consciousness. So as we've been alluding to, many people have ideas about consciousness, where it resides, how it functions. So everyone from Chalmers to Damasio to obviously Mark has made some pretty extraordinary research on this in terms of finding it in the midbrain, in the brainstem, which is fascinating stuff there. And Seth. I mean, there's a bunch of people that have been talking about consciousness. It's sort of trendy. How do you, based on everything we've discussed, Bayesian brain, free energy principle, can this tell us anything about consciousness more accurately or more clearly about what it could be, where it could be, how it functions? What is, I guess, your kind of stamp on this topic in terms of consciousness?
I think the first thing to say, which is often said by philosophers, is that the free energy principle is not a theory of consciousness. That sounds slightly deflationary, but in fact it's quite a useful thing, because if it's not it wasn't designed to explain consciousness, and certainly people like me have no pretensions to try and get into that game, but it would be very interesting to see if it holds the formalism that allows people to address certain hypotheses or questions about consciousness. So that is deeply engaging. And just for your interest, there's currently just been funded a John Templeton Foundation collaborative adversarial collaboration to play off active inference against integrated information theory. So there are lots of academics and theoreticians out there who are sort of interested in what more formal accounts of sentient behavior will bring to the table in terms of answering questions about consciousness. So everything I am saying is contextualized by the fact that the free energy principle is not there to explain consciousness. But if you had to answer some of the deeper and more challenging questions, such as David Chalmers' hard question, and or accommodate some fundamental dialectics, Cartesian dualism, for example. What space is on offer from the free energy principle? And I think there are some quite clear answers there. We can take this from a number of directions. I'll take two because they follow on from some of your pressing questions about sort of drives, from the Freudian perspective. So what would drives look like from the point of view of the free energy principle? But let's not talk about the free energy principle. Let's talk about active inference as an actual process theory for you and me that are, if you like, conforming to the free energy principle. So the first thing that one has to note is something we've spoken about before, that we have a calculus for beliefs about something. That immediately introduces a duality in terms of interpreting internal brain states. We can either talk about the probabilistic population dynamics and the information of neuronal populations and their activity, which would be intrinsic to the brain. How likely is it that my neurons are going to fire with this particular pattern in this particular part of the brain in this particular circumstance, which of course is one of the key questions that we address with neuroimaging. Or you can, under the free energy principle or active inference, say, well, hang on a second. There's another kind of probability structure, a belief space, because we've just said for every pattern of neural activity, there is encoded an implicit representation of beliefs about the outside. Now, what that means is technically that not only is there a probabilistic description of my neuronal activity, but that neural activity is equipped with something called a statistical manifold, by which I simply mean that every point on this manifold that corresponds to a pattern of brain activity is equipped with a belief structure, a belief distribution, a Bayesian belief about something else, about the outside, about you, the causes of my sensations. And that means that I can now talk about an information geometry of a different sort, which is now about the outside, an extrinsic information geometry. And that's quite a nice picture, because this notion of belief updating we've been talking about, Bayesian belief updating, corresponds to a movement on this statistical manifold. So you imagine that every pattern of activity in your brain corresponds to a point on this abstract manifold, this surface in a very high dimensional space. And every time the pattern of activity changes in virtue of your neuronal dynamics, you make a movement on that space. And that movement is belief updating. It is exactly the same as moving from the prior to the posterior that we were talking about before. So sensations come in and they move the point on the statistical manifold to produce the belief updating. So you are literally now describing mathematically with an information geometry belief updating and the process of inference. And the key link here is that the measures, the metrics that define this information geometry of belief updating are something called Fisher information metrics. And mathematically, they correspond exactly to the precision we were talking about before. So technically, it's the curvature of that space as measured by the uncertainty or the precision of your belief updating. So there's an intimate relationship now between the precision that we were talking about in relation to, say, Mark Soames, and just to slip in here, that the cells of origin of those neurotransmitter systems that control the postsynaptic gain that mediate the precision are exactly in the midbrain structures that Mark thinks is the seat of consciousness. So this is all entirely internally consistent. But it's also consistent with the Freudian notions of drives, because you can think about this movement on the statistical manifold, this belief updating, as being driven by forces. What are these forces? They are the prediction errors. They are the surprises. They are the effect of the likelihood on the priors that force it or move it to produce the posteriors. So now we have this notion, very elemental notion, of a drive, probably sort of oversimplified from a Freudian perspective, but I think the mechanics sort of holds true here. That the drive is literally the thing, the role of the prediction errors in driving belief updating from prior to posterior beliefs. But crucially, we now understand this force, this drive, as being gated or nuanced or contextualized by the precision, which brings us again back to the fundamental importance of getting this sort of metacognitive beliefs about beliefs or predictions of precision right, in terms of enabling those particular forces and drives to be manifest in the way that we both organize our neural activity, but also explore our belief space by moving around on the statistical manifold. So you can write this down very precisely in terms of information geometry. There's lots of really interesting maths that gets right into the world of gauge theories and the like, all telling the same story. That the potency of these drives depends upon the curvature, and the curvature depends upon the precision or our beliefs about the uncertainty. The point here, though, from a sort of consciousness point of view, is that there are two descriptions of movement on this statistical manifold. There's a description from the extrinsic perspective in terms of the probability distributions encoded by a point on the manifold. And there's another intrinsic description, which is the simpler one, just about the probability of having this pattern of neural activity. So there are people, I'm thinking about colleagues such as Vanio Weiss, who together have put this forward as a way of repairing dualism. That you've basically got a dialectic for free mathematically in the information geometry that jointly ascribes a particular physical instantiation in terms of neuronal activity and patterns of neural firing to any point on the statistical manifold that is accompanied by beliefs about something else, which would be the sort of the more mindful aspect of a Cartesian divide. So you've got this sort of a monistic account that has these dual aspects of mindful belief updating and the physical embodiment of that. That I think it would be a potentially useful way to talk about sort of dualism versus monism when it comes to some possibly historic, but to my limited understanding, sort of foundational issues in consciousness research. That would be sort of one, if you like, opportunity for the Bayesian mechanics afforded by active inference and the free energy principle to produce some quite clear predictions about the relationship between mindful stuff and brainful stuff, where there has to be, if you like, a convergence within this information geometry. The other thing it brings to the table is that it is the movement on this manifold. It is moving through a belief space. That is the essence of inference. So if you remember, the free energy principle is just trying to describe the dynamics of a system that has a non-equilibrium steady state solution for a certain amount of time. Inherent in the use of the word dynamics is you're looking at a process that is unfolding in time. What that tells you is that if you want to talk about consciousness, then it may be best to think of consciousness as this process of belief updating. in exactly the same spirit that we talk about evolution as an evolutionary process. We don't talk about the state of evolution at any particular time that's divorced from the dynamics, the paths, and the process itself. The process of evolutionary selection, as opposed to, say, selecting a plan or a particular belief, or or updating my beliefs in terms of the process of inference in under the Bayesian Brain hypothesis. We talk about the process as unfolding in time. So what that would mean, if you just translate that perspective, which is inherently dynamical, to consciousness research, is that questions about what it is to be consciousness have to be recast in terms of what processes must you evince in order to qualify as having a conscious process. So states of consciousness and levels of consciousness are only meaningful when they apply to something that is changing in time, essentially moving on this on the statistical manifold. So that's, from my point of view, a couple of things that are brought to the table by having a formal mechanics or calculus underneath belief updating, to have a calculus of sentience, a physics of sentience that tells you immediately you're talking about processes. And of course, if you think of, in terms of any optimization, or casting things in terms of any optimization, then you are talking about the process of optimization. And indeed, even from the point of view of the semantics of things like variational principles of least action, the leastness, the minimization aspect of it talks again to a process that is playing out over time. So that would certainly be, if you like, one constraint on offer for anybody who talks about consciousness. Are they committed to a way of thinking about consciousness that just doesn't have any meaning in the sense that it's about a particular state of being? Or can they recast or formulate their hypothesis in terms of a process? The third level, or the third sort of thing on offer with active inference brings us back again to the generative model. So remember, previously we were talking about differences between thermostats, flies, mice, and men. And I was very comfortable talking about those differences from a unique perspective, which was simply, what are the differences in the generative models? So if you can boil everything down to the evidence for which you are trying to secure, which is the generative model, then you can start to talk about different kinds of consciousness in a graded way in terms of different kinds of generative models. And we've already had this conversation in the sense that, I can have a generative model for a thermostat, which is temporally very thin. It has just very, very limited temporal horizon, and then we graduate to particles and creatures that have a more allostatic as opposed to a homeostatic way of engaging actively with their environment, that acquire a certain temporal depth, and then we move on to the opportunities when you now have a generative model of the future for different outcomes, different counterfactuals, and then we move into Anil Seth's notion of counterfactual richness. But noting the counterfactual richness as one way of understanding consciousness or a conscious process is only allowable when your generative model has the capacity to model counterfactual outcomes in the future. And then we get to the remarkable counterfactual outcomes that underwrite things like the philosophical zombie and brain in a vat, and then we can start to talk about we can go from mice to men to philosophers, and then start to engage with that kind of conversation. So that's another sort of structural, architectural, formal thing or way of dealing with these questions that you get from the physics and the mathematics, which wouldn't otherwise be there if you're just using narrative arguments and historical arguments.
I was going to say, you were talking about this convergence, and as you were describing that, I was thinking about how there is a kind of multidimensionality or a continuum aspect of this being a process of things, as opposed to just this static kind of state, which I think, based on many of the things I've read on consciousness, that makes a lot of intuitive sense. And I think the way that you're talking about this underlying calculus to try and describe a kind of process makes a lot of sense. In terms of artificial intelligence, so maybe we can make the leap even further, right? Mice to men to philosophers to AI, right? Obviously there's it's sort of connected with the consciousness question, although you could make artificial intelligence that doesn't need to be conscious. I don't think it's a prerequisite, although some people may argue about this. But in terms of, again, this underlying calculus that is there with the free energy principle, what is it, I guess, specifically, or something that gives it this uniqueness that can give us information about artificial intelligence? Obviously, artificial intelligence is a very broad categorization. So, I mean, my dishwasher and microwave is a form of artificial intelligence, right, at a very, very low level. And then there's artificial intelligence that we see in science fiction stories, such as, humanoid robots that are sentient and they maybe have feelings and, things like that over time. So there's the whole gamut here. And of course, you could make the offshoot of, well, first you have to define intelligence, which is a very long footnote, which we don't have to do, although if you want to, I would totally be fine with you explaining that as well. But just how do we understand the elements of free energy principle for artificial intelligence now, and how it could have potential utility as we continue to grow and expand our mechanics or computational aspects of artificial intelligence?
Part of your question was, how does the free energy principle give you the opportunity to get more information about the nature of intelligence and as you intimate, sort of artificial intelligence. Interestingly, that getting information about is actually at the heart of the answer I'm going to give you. So the answer I'm going to give you, I'm going to foreground, though, one key thing, which is in response to a previous question, what's the free energy principle for? Very much like the theory of natural selection, it doesn't really do anything, I'm afraid. It's very pretty, and you can have philosophical debates about it, which I'm sure we'll come to. But why is it useful? And the answer is, if you read the free energy principle as a mechanics that is apt to describe systems that have solutions to their non-equilibrium steady states in terms of an inference process, then the answer is it's pretty, it is not useful. However, once you know the functional form of the equations of motion, the dynamics, the updating, that have to be in play in order for the system to be intelligent or to show a self-maintaining or autopoietic-like behavior, what you can do is write into an artifact the generative model and all the prior preferences entailed by that generative model to simulate an artifact that has the same properties of self-maintaining and maintaining its Markov blanket. Why would you want to do that? Well, I think there are two cardinal reasons why you might want to do that. Why would you like to build a Markov blanket maintaining building machine that's doing inference? That it basically is realizing the principle of least action that prescribes the differential equations that you would write into a computer simulation, or indeed a robot, or an artifact that was supposedly showing artificial intelligence. Well, I think there are two reasons to do that. One, you might want to build an active inference agent, an artifact that's actually doing active inference. How would that differ from artificial intelligence as we currently know it? That's a really good question. There are very clear answers, and I'll give you those answers in a second. But just to conclude this part of the answer with the second motivation, that you might want to build synthetic agents with synthetic sentience under the variational principle of least action that is the free energy principle, is you might want to make inferences about somebody else, and I'm now thinking from the point of view of a psychiatrist, you might now want to try and simulate choice behavior and active inference under a particular model, and then adjust the preferences and the priors of that generative model until you reproduce the kind of observable behaviors that this patient has or this particular cohort shows. So what we're talking about here is essentially using the simulation models as observation models of real world people and other creatures in order to try and understand their internal dynamics and their internal mechanics. There's something quite fundamental about that particular take, because remember before we talked about the Markov blanket enshrouding the internal states of something from the external states, so that there is, if you like, an impenetrability. There's a fundamental statistical divorce between the internal states and the external states, meaning that the external states are hidden from the internal states. But the converse is also true, which means that from the outside, the internal states of any creature or person or loved one are forever hidden from you, from the outside. So you can only ever infer the machinations and the dynamics and the belief updating on the inside, which is interesting because that means, much of my day job in neuroimaging is trying to peek behind the Markov blanket to see what's going on, but you can't do it properly. Otherwise, you'd have to breach the Markov blanket to become invasive or study dead things in order to try and infer what was going on. So that means that you need to use inference just to understand the internal dynamics of a brain of a person, which means that the only way you can do it is to have a generative model of a generative model, which means that now you've got another use case for active inference in the free energy principle, which is building models of people and patients and then adjusting them until you use the adjusted model that renders the behavior of the model very similar to the behavior of the patient to infer this is how the patient works, or at least this is as if an as-if explanation or account of this patient. So those are my two principal motivations, to use these as a principled model of choice behavior or neuronal responses that I can measure empirically to answer my hypotheses about how the brain works. There is another agenda which we've touched upon, which is more the fun of creating artificial general intelligence or general intelligence or AGI, and the distinction between artificial intelligence and AGI, or the next wave of artificially or intelligent artifacts, I personally do think is staring you in the face. In terms of what the difference is between active inference under more sophisticated generative models that have the ability to model the consequences of action. So if the end point of this argument is that if it is the case that I have to minimize my prediction errors or free energy, or at least look as if I am minimizing my prediction errors or free energy just to exist, if it is an existential imperative for existence, then a priori, I must also believe that every action that I choose, every choice that I make, must be that which is the most likely to minimize prediction errors or free energy after I've made that action. So the consequences of my action are now scored in terms of their ability to reduce the free energy I expect following an action. So then what you can do mathematically is just look at the expected free energy and ask, how could I interpret that? What does it look like? What are the qualities? What are the first principal accounts of a good choice or a good action. And when one does that, it looks like, as you might expect, there are a number of different interpretations of this expected free energy, which is a big thing that active inference brings to the table. So this is an objective function that now replaces utility functions in reinforcement learning. It also replaces the principles that underlie active learning and things like optimal Bayesian design, in the sense that it grandfathers these things and puts both of those two aspects of good behavior together. And in putting them together, this objective function that underwrites the right choices, the right behaviors, is just expected surprise or uncertainty, which means that all I need to do is to choose those behaviors that minimize or resolve uncertainty or maximize information gain under prior preferences inherent in my generative model. So that last statement is quite crucial. And what it transpires to be, the expected free energy transpires to be a mixture of two components, one of which is an epistemic information hungry seeking component, and the other one is a more pragmatic preference seeking component. And put them together, they are just then minimizing overall uncertainty or minimizing the expected free energy. Crucially, that epistemic information seeking component is the thing that underwrites curiosity. So if you look at the artificial curiosity literature, the key problem has been, how do you articulate and mathematically formalize the drives to resolve curiosity, the sensation seeking, the inquisitiveness that characterizes all of us, certainly in the context of this conversation, but I think all of us as little scientists just need to live. We have to be curious creatures. And the expected free energy is basically that curiosity, that intrinsic motivation. That's another word in neurorobotics, developmental neurorobotics, also known as expected salience. And it puts it together with the surprise minimizing aspects endowed by having prior preferences in your generative model. I expect myself to do this kind of thing or encounter these kinds of outcomes. But because I'm contextualizing that with this information curiosity seeking component, I've now got a complete objective function that essentially equips active inference agents with curiosity. So that is what is missing in AI, that no Alexa or no iPhone is ever going to ask you a question because it's curious about you. So the next generation of artificial intelligence will, if it complies with the variational principles of least action as articulated under active inference, should show a genuine interest in you, because it will act, or it will select those questions and those actions, or look at these websites or these data, engage in this kind of data mining, simply to resolve uncertainty about its generative model of the world. And if its generative model of the world contains you, it'll want to know about you. And it will ask the best kinds of questions that will maximally resolve its uncertainty about you. So it'll be genuinely interested in you. And in that sense, then I think because it's got this curiosity inherent in its selection of its actions, I think it will then show a kind of artificial intelligence that is much closer to the generalized artificial intelligence that people have been aspiring to. But it does rest upon putting the curiosity in as part of the package when minimizing the expected free energy.
I have this chilling fantasy in my mind as you're telling me this about, my Alexa or my Siri on my phone asking me questions about just a very, very chilling kind of thing about it. But I do agree with you. I do think that that's probably the the next step, the next place, because of how good algorithms are at trying to predict based on things that we're searching or looking or things like that. It's trying to accurately get something. If I put a search in Google now, it takes, not even 2 seconds, right? 10 years ago, it took longer, and you have to find all these things. And it's trying to curate the things for you that you're searching. I could imagine that there's more of a, not just that the AI is receptive, but then expressive in what they're trying to ask and inquire of you, the person that's searching, which is, there's a little bit more, you're right, there's like more of a two-way street there, which is definitely, it's a little bit of a scary thought to think about. I think there could be really cool utilities to it, but I definitely think there's obviously, like many things, an inherent danger. Before, I want to ask you about the imaging techniques you've done, because that's, as you say, your day job is that's what you do, and obviously you've been prolific in those areas. I just want to ask one thing, just because it's relevant now, and I think as we continue moving throughout this second decade, I guess, of the 21st century, is about your work with COVID-19. And I know this is a big area, big topic, and a lot of noise about the pandemic in all aspects. I just want to ask you, just generally, you can briefly just summarize, kind of how, what your work was, I believe, was with uncertainty and predictive models and how we understand things and how we understand certain types of immunity and things like that. Just kind of how you became involved, or how you think about the pandemic and COVID, and how you've been doing work in that area.
Yes, of course. So, the answer to that question does come from my day job, which is using brain imaging and empirical data acquired through a variety of different ways of peeking or breaching the Markov blanket, or look inside people's heads. So you can do that with things like functional magnetic resonance imaging, which gives you sort of whole brain images every second or so, and that reports fluctuations in coarse-grained neural activity in different parts of the brain, right through to things like magnetoencephalography and equivalent EEG procedures, which give you a much temporally resolved picture or signals reporting electromagnetic fluctuations in neural activity over fractions of a millisecond. But the price paid is that you lose the spatial resolution. But the point being is that these are ways of looking at the brain in action and affording data, empirical evidence for various hypotheses about the underlying functional brain architectures, of which we have been talking a lot, sort of the hierarchical architectures, the recurrent message passing entailed by different, say, predictive coding or other theories. And in particular, certainly from my perspective, trying to understand the failures of those architectures in terms of false inference that ensues from, for example, breaking the precision control that we've been talking about, and how that might show up in people, for example, with schizophrenia or depression or other neurological or psychiatric conditions. So that's my day job. And the link to the COVID research is quite easy to demonstrate, in the sense that what you are talking about when looking at a message passing architecture, a neuronal message passing architecture that is doing the belief updating, that is enacting the drives afforded by prediction errors in doing the belief updating and causing activity in different parts of the brain. This obviously can also be expressed as a communication and a dissemination of information or influences. So you've got the spread of messages, bits of information from one neuronal population to another neural population. In order to make sense of the brain imaging data, you actually have to have an underlying generative model of this process. And now we're talking about a generative model of the brain that I, as a scientist, are using to make sense of my scientific or empirical data that comes from the brain imaging. And I deliberately phrased the fundaments of these generative models in terms of spreading information among neural populations, because of course that is exactly the same kind of generative model you'd use when trying to model the spread of a virus amongst the populations that constitute a country or a region or a city. So my involvement in the modeling of the coronavirus epidemic comes straight from the observation that the generative models, the state space models, the convolution models, these are just technical terms, and the kinds of models that we use to make sense of brain imaging time series generated by populations of neurons could be very quickly and efficiently repurposed to make sense of the epidemiological time series generated by populations of people that were in various states of infection, symptomatic, vaccination and the like. So for the past 2 years, my weekend job has now been split between something called Bayesian model selection or structure learning, which is basically fiddling with your generative model until it minimizes its free energy or maximizes its marginal likelihood in relation to the data that's incrementally becomes available, and different kinds of data on the one hand, and then trying to do the free energy principle and make it simpler and more accessible on the other hand. So that's how I became involved. Different levels of engagement, working as a panelist on the Independent Sage, which was a sort of a public-facing version, or was meant to be a complement, a public-facing complement to the scientific advisory group on emergencies that was supplying the Cabinet Office and the government with advice. We were much more, in its original formulation, a sort of public service-facing information dissemination and public engagement sort of initiative run by academics. I have been involved on other advisory bodies, largely motivated or resting upon the predictions made by technically what's called Dynamic Causal Modeling of the time series data that allows you to optimize the parameters of that generative model, given all the data you have up until this point in time, and then run the model forward sometimes under different scenarios that allows you to make sort of forecasts about what would happen if I did this or did that. That can be useful for nuancing the advice given to politicians and decision makers when considering, should we relax lockdown rules at this point? Should we encourage this age group to take up vaccines, for example?
Yeah, no, that's super salient and instrumental. So that's incredible work. So we've already kind of talked about it. So let's get into your day job. you're with the imaging techniques. So the thing that I think is your initial claim to fame here is the statistical parametric mapping, and then I think also subsequently the voxel-based morphometry. These are the two imaging techniques. Most people will know a CT scan, an MRI scan. I do want to ask you about fMRIs. Some people may know about diffusion tensor imaging. There's all different types of ways of scanning the brain. So maybe just tell us what these two things are, the statistical parametric mapping and the voxels, and then just kind of how that sits in with mapping of the brain overall.
Right. Well, you introduced the notion of a CT scan, and then many people will also be familiar with X-rays, images that peek behind the curtain and get on, give you a picture of what's going on the inside. So statistical parametric mapping can be conceived of as producing X-rays of significance, of significant activation. And by activation, I mean a change. So going back to this notion that the interesting stuff is in the processes, from the point of view of the free energy principle, the belief updating. So you needed a way of forming X-rays of a certain kind that reported where the belief updating and the neural activity and the hemodynamic or the blood flow consequences of that hemodynamic activity, where and when they were occurring in the brain. So SPM, or Statistical Parametric Mapping, is just that. It's just the construction of X-rays or CT scans where the values of the image at any point in the image, usually known as a pixel or a voxel, correspond to a statistic testing a particular hypothesis about the pattern of the fluctuations in neural activity, over which you have usually some experimental control. So when people talk about activations, what they basically mean is, have I been able to evoke neuronal or belief updating and neuronal message passing, and thereby neural activity and everything that supports that neural activity by presenting this kind of stimulus to the subject relative to that kind of stimulus. So you're just comparing the evoked responses over time and then summarizing those differences in terms of a statistic, and then putting that statistic for that part of the brain into an image, and thereby creating a whole brain map or a statistical X-ray of the functional anatomy. So it's now, unlike a CT scan, which is the structural anatomy, this is now the functional anatomy, because you're, if you like, summarizing a functional process. And very similar approaches are taken to in EEG or electromagnetic and electrophysiological procedures. You mentioned voxel-based morphometry. That is simply the application of this statistical X-ray, this SPM-like technology, to the special case of sequences of structural images. So you're normally in the game of trying to infer, did this group of patients, say with Alzheimer's disease or Parkinson's disease, do they show a systematic difference in their structural anatomy? Again, in this instance, using an SPM or a statistical X-ray, but in this instance, the statistic is reporting the significance of the difference in the composition of the anatomy as measured with magnetic resonance imaging, usually, or could be CT scans. But using here not time series data, but usually data points from multiple subjects that are carefully selected.
So it sounds like there's an integration of, or trying to have the integration of, looking at the functional pieces in time of a process for a structural picture, is what it sounds like it's trying to do. How you use this for schizophrenia, particularly? How did you use these methods to understand more schizophrenia, and how literally the images of the brain for individuals with schizophrenia, how it looks and how it functions, and maybe just talk about that as well. I'll just, as a footnote, I worked inpatient with individual and outpatient, but inpatient with individuals that have schizophrenia. So I've been around these folks for a good part of my career, and they're very, very fascinating individuals in terms of personality, in terms of their cognition, in terms of their brain functioning, and being on plenty of treatment plans and big long meetings with psychiatrists and neuroscientists, trying to understand schizophrenia, but then also understand and how to try to provide clinical services to individuals with schizophrenia. So I'm curious as well, personally, almost of how did you use these techniques to try and understand specifically individuals with schizophrenia?
Right. Again, that's an excellent question, and it speaks to the motivation for much of the theoretical work that we've been talking about. So understanding what has gone wrong in certain people, qualifying this, of course, so the schizophrenics would not like you to think that their brains have gone wrong. So
that's right. That's right.
The therapist's assessment.
Right. They just have a different reality. That's all.
Exactly. In fact, that's mathematically true by the complete class theorem, but that's another story. So the way that all this fits together is in terms of understanding much of psychiatry and many neurological syndromes in terms of false inference. And if you can understand the experiences of a psychiatric patient in terms of false inference, then now we already have a mechanics that is what we've been talking about, active inference, the free energy principle, and predictive coding, Bayesian brain. We already have a mechanics at hand to ask at what point has there been some aberrant message passing or belief updating that could lead to this false inference. So you may be asking, well, why on earth would you want to cast all of psychiatry as false inference? Well, it's a very natural way of accommodating that. That's where the symptoms lie. That's where the ontology of psychiatry lies. It's in belief updating. It's in beliefs about the world. So when I talk about false inference, I mean it in a simple sense of type 1 and type 2 errors, false positives and false negatives. So when you think about, say, an hallucination, what is that? Well, it's just inferring something is there when it's not. It's just a type 1 kind of false inference. What about neglect syndromes, agnosia, dissociative syndromes? They are just false inferences of the second kind, inferring something is not there when it is. And I think, if you think about it, nearly all psychiatric conditions can be construed in this way, either falsely inferring something is there when it's not, and vice versa. So what that means is you now move on to the more challenging and pragmatic questions. Well, what could account for this kind of false inference? And the questions then can be posed either to the structure of the implicit generative model that is entailed by our brains, or the process theories that undergird the message passing and the physiology of that message passing. And what you're basically talking about is a form of disconnection. Now, this disconnection may sound odd to talk immediately about disconnection, but remember, the architecture of any distributed system is defined by its connectivity. The very notion of a hierarchy depends upon the absence of certain connections that would otherwise transcend levels in, say, a linear or subsumption hierarchy. So connections are everything in terms of sculpting and defining the architectures that endow the brain with an implicit generative model of its lived world. And furthermore, the message passing that enacts the drives, the belief updates, the precision weighted predictors that we've been talking about, those are just expressions of influences from one part of the brain to the other part of the brain. So it's all about the connectivity. And that means that you need to now use the empirical data in a way that enables you to answer questions about disconnections. And they can come in many flavors. As a neurologist, subscribing to early ideas of disconnections from people like Geschwind in terms of lesions to the organs of connection in the brain, the white matter tracts that connect, the long-range fibers that connect different parts of the brain. These can be sort of macroscopic disconnections. From the point of view of schizophrenia research, that idea was first proposed by Wernicke, who was famous for his studies of specialization, functional specialization in the language system. But his big gift in terms of psychiatry was the surjunction hypothesis, that you could understand dementia praecox or early formulations of schizophrenia in terms of disruption to these the organs of connectivity, the white matter tracts that we currently study with things like diffusion weighted magnetic resonance imaging or tractography, that based upon that kind of imaging. But there was another perspective which most people ascribe to Bloiler, which spoke more about the sort of the fine-grained disintegration of the psyche, the loss of coherence and literally a dissolution at the level of mental life. So from our perspective, that would be belief updating, which one might nowadays understand much more as a microscopic disconnection at the level of synapses, the little specializations, the little buttons that, or plugs that connect one neuron to another neuron. At the end of the axon, or the long fibers that emanate from a particular neuronal cell, there's a whole bunch of pre and postsynaptic specializations called synapses, which you basically in the little plugs at which all the neurotransmitters act. So in clinical neuroscience, a failure of, or a disconnection, or a failure of integration at the synaptic level will be known as a synaptopathy, a pathology of synaptic connections. So that's the kind of disconnection that most people have now in mind when thinking about the abnormal message passing that might produce the false inference that is characteristic of different psychiatric conditions. That means you need to be able to measure this. You need to have an in vivo, in-life way of measuring the synaptic efficacy, the connection strength, the gain that we were talking about before, that is modulated through the precision engineered message passing, getting the excitability right. These are all different ways of expressing the synaptic efficacy, the strength of connections in the brain. And if you think that things like schizophrenia are manifestations of false inferences that inherit from a very pernicious and particular kind of synaptopathy, which precludes getting the precision right, getting the excitability of, say, for example, neurons reporting prediction errors correct, then you need to be able to measure it. And that's where the third technical contribution to brain imaging comes in, which is the dynamic causal modeling that was used to study the pandemic. So we use the dynamic causal modeling to basically study the spread of viruses from person to person. But it was originally devised to study the synaptic efficacies that underwrite the spread of signals from one member of a neuronal population to another one. So that's where it's at the moment. I mean, it's difficult for me to really summarize, what we were doing and what we are doing in a nutshell, because a bit like your first questions about how much I have achieved in my career, I think this field also, it's a long journey and it's very incremental. And sometimes you're quite surprised by how far you've moved. But if you look at the progress from this year to last year, it's almost zero. You have to look over 20 years since the inception of, from my perspective at least, dynamic causal modeling. That was explicitly done in order to understand disconnections and synaptopathies in schizophrenia, because that's where I came from in psychiatry. Then it's about now that people are starting to take this technology seriously and start to apply it at scale, and in a way that is underwritten by companion studies of the same systems in different models in cell cultures, for example. So if you've got one generative model under the hood that explains disconnection of a certain kind due to this synaptopathy, which we're now associating with abnormal precision control, of exactly the same kind that Mark was intimating when he's talking about his broken midbrains, because these are the ones that broadcast the signals that control the synaptic efficacy. In exactly the same way as you might imagine that happening in Parkinson's disease, where you've got abnormal, a hypodopaminergic state, the complement in schizophrenia being a potentially hyperdopaminergic state, and many other conditions. So that application of dynamic causal modeling at different scales and across scales is now starting to emerge, at least in proposal form. No one yet has had the nerve to fund it. My hope is in the next year or two, there are a sufficient number of proofs of principle that it now becomes a viable way of proceeding. And just to bring things to closure, the two areas that seem to that have really exploited this way of making sense of data to get at synaptopathies are epilepsy research, in particular childhood epilepsy, and some neurodegenerative conditions. So that's where the action is at the moment.
Yeah, I could definitely see that. I want to ask just as since this is your kind of you're closer to this, is about fMRIs. Just as a small side here, many people were very excited about fMRIs when they came out. You know, this is very literally colorful and exciting in some ways. But over time, I guess over 30 years now, I mean, there are some people that would say that it's a kind of, you know, modern day phrenology. Do you agree with that? What's the utility of fMRIs, if anything? And, you know, how good is it really at translating into, I guess, better treatments? You know, because, you know, some area, because we know with diffusion tensor imaging that there's all of the brain is connected. All of it is linked up. All of it is talking with each other. Different parts of the brain, cortical, subcortical, different lobes, everything's talking to each other. So how do we understand, I guess, the utility of fMRIs, if at all? And how could it translate, I guess, into better treatments?
So you say some people are starting to call it a sort of latter-day phrenology. In fact, they were calling it that at the inception of so the new cartography, the neo phrenology, right. Which is a fair critique. So I think the answer to that question is a little bit like this, you know, how far have we come in our journey? If you ask year by year, yes, the advances have been incremental at best. But if you just look back with a temporal resolution of decades, fMRI has had quite a profound impact on the clinical, cognitive, and translational neurosciences. So simple things which people of your gentle and tender age will not be aware of, simple things that you take for granted, were just hypotheses in 1989, 1990. For example, the whole notion of functional specialization in the brain that underwrote sort of Fodorian modalities and all sorts of hypotheses about, in fact, also subtended neurophrenology, the notion that one part of the brain did this and another part of the brain did that. So this is a notion of functional specialization, in particular segregation, that this particular functionality was segregated anatomically or spatially to this part of the brain. And that therefore we had at least a good hypothesis about the predictions that would ensue following brain damage, and we can make some guesses about the importance of connectivity under the functional segregation hypothesis. No one knew, though. No one, up until 1989, no one knew that there was, for example, color specialization in this particular part of V4 that was segregated in the sense that there was no color-related responses elsewhere. And you couldn't do that because you'd have to have electrodes everywhere in the brain in order to show that it was this part of the brain responding to color and not that part of the brain. So it's only in the early 1990s that people could actually, after about 200 years, possibly 150 years, confirm the original hypotheses about functional localization and specialization and segregation in the brain. That was a profound thing. Sure. As I say, from your perspective, you just assume that people in the 1980s believed that functional specialization was a principle of brain organization. They did believe it, but it was just a hypothesis. And there was doubt. After fMRI, there was no doubt. It was just part of the foundation of neurophrenology. But the second sort of big point to make is that, you know, if you want to understand how a virus spreads, or how a meme spreads, or how messages spread in a deep neural network, or how belief updating operates in a functionally segregated and specialized hierarchical brain. You have to have a way of identifying the things that are connected. So if you are truly a cartographer, when you go to a new country, the first thing you do is identify the landmarks before you start worrying about the communication, the rivers, or indeed if it's a developed country, the routes of communication, the rail links and all of that good stuff. The first thing you do is have to identify what's happening where in terms of these functionally segregated definitive aspects of any map, or before you can talk about distributed processing. Well, distributed amongst what? Well, amongst the functionally specialized areas. Well, where are they? We can now identify those using fMRI. But of course, that's just the first step. So within about sort of 5 to 8 years, people were turning their attention to the real question, which is back to the connectivity. It's back to the principles that underwrite the distributed processing, as you say, understanding why every part of the brain seems to be connected, at least with 2 degrees of freedom to every other part of the brain. So that's where the big questions were, and subsequently addressed in terms of fundamental distinctions between things like functional and effective connectivity. There was a period when all the excitement was about sort of measuring correlations and functional connectivities in the brain. But throughout that period, of course, things like dynamic causal modeling were being developed in order to measure the actual directed coupling that subtended these correlations that people were measuring with functional connectivity. So was fMRI, or is fMRI useful in that regard, and has it had any material effect on sort of treatment? I mean, I could cite particular examples in terms of epilepsy research and the identification of sort of eloquent areas, the use of imaging as a biomarkers in, say, genetic studies of predisposition to various illnesses. I could give you a number of some sort of quite compelling but very colloquial examples of where it has worked. I would sort of concur with you that there hasn't been an awakening of insights. It's more a consolidation of what we have known from centuries of careful neuroanatomy and neurophysiology, an ever-increasing fine-grainedness that allows us now to talk about the particular subreceptors involved in a particular syndrome that underwrite the synaptic or the synaptopathy that's producing the disconnection in this particular system, say the interoceptive system involving the anterior cingulate and the anterior insula. So it's really people really drilling down on the fine grain in certain quarters of neuroimaging. There's a lot of B grade stuff as well, but the A grade mechanistic theory-driven applications, hypothesis-driven applications of neuroimaging, really has advanced quite remarkably in the basic neurosciences. Whether that has yet to translate into clinical neuroscience, I think that's an open question. But the answer, I think, will only reveal itself when you look back and say what's happened in the past 10 years, and then you probably get a much more positive response than otherwise. Just one final comment. It certainly is the case that fMRI, as an imaging modality, has lost its shine in the sense of its appalling temporal resolution, which means that most earnest imaging neuroscientists or cognitive neuroscientists, or indeed clinical neuroscientists, would want to supplement the cartographic gift of fMRI with highly resolved electromagnetic, electrophysiological responses. So, anybody doing any serious imaging neuroscience nowadays would also recourse to electromagnetic signals and understanding distributed processing at that level, guided by the cartography on offer from fMRI.
Yeah, no, that's important to also keep in mind as well. Well, my last question for you is I guess sort of a big one. There's 2 parts to it. So the first part is you've talked about many of your theoretical principles. You've talked about some of the stuff from the imaging techniques. So we've talked about the Bayesian brain, which has some utility, or has many utilities, but many people are starting to talk more about it mainstream, and have been for many years. But in terms of your free energy principle and how you use this with active inference, predictive coding theory, how do you think this can be translated to the common person? Right? How can people use these wonderful theoretical structures and frameworks in a way that's applied and has some pragmatic utility, in ways that everyone can kind of grasp and say, oh, yes, I got that, and I see how this is really important, or use it in various clinical practices in whichever domain, in psychiatry, neuroscience, and psychology, et cetera. How do you think the ability to translate those models and theories into practical applied use is key, and ways to do that? And then larger frame of this is for neuroscience as a whole. How do you see in neuroscience, its utilities, maybe some of its limitations, but how it's useful for people to continue to understand the complexities of neuroscience?
In a sense, we've already sort of covered, I think, the two key practical applications, and perhaps it would be appropriate just to rehearse the point that there's a lot of similarity between the free energy principle and the theory of natural selection. In and of themselves, they do nothing for you. You've actually got to want to answer a question in a particular situation, or to build something in a given circumstance. And then, the free energy principle and its attendant process theories will certainly provide you the functional forms and the architecture and the mechanics to do that quite quickly and efficiently. So the question now is, why would you ever want to build those things, and how could you practically use them? So in terms of building sentient artifacts, I just remind myself and recall an earlier part of the conversation that what we have now is an off-the-shelf set of belief updating schemes that should, in principle, create curious sentient robots and artifacts. That will be, to my mind, the next step in artificial or machine learning. And I say that from a number of perspectives. First of all, in terms of what is a use case that will be appreciated by members of the public? I generally think that it's probably going to be the manufacture of little pets, as much of sort of public-facing AI has pursued. But the difference will be here. These artificial pets will actually have a curiosity, and it'll be much easier to project and anthropomorphize and to apply theory of mind to these kinds of little curious pets. And so they'll become increasingly more like your actual favorite pet or your dog, simply because they now have curiosity under the hood. So that's how I personally think people are going to make money out of active inference. It's just equipping these little robots with a bit of curiosity, or to use Jürgen Schmidhuber's phrase, artificial curiosity. And interestingly, mentioning Jürgen Schmidhuber, of course, he thinks that's the essence of creativity and fun. It's this curiosity, this epistemic drive, this information-seeking part of resolving uncertainty or maximizing information gain through actively soliciting evidence for your generative models of the world. In terms of machine learning and the more, I think, pressing and less trivial issue of sustainability, the whole point of active inference is that it is Bayes optimal in the way that it gets data and assimilates those data, and that optimality expresses itself in certain kinds of efficiency, which I think are going to be very important in terms of sustainable computation and energy use. So I've heard that in 2025, about 20%, if not 22%, of the total energy consumption globally will be by data farms and e-commerce and exchange. So this is a really, if you like, thermodynamically and climate change relevant observation that there are good ways to make inference and to data mine, and there are bad ways. Now, the good ways are those that conform to Hamilton's principle of least action. That's the free energy principle, that you minimize in your process of inference or active inference, you maximize the evidence, which mathematically simply means minimizing the complexity with under accuracy constraints, where the complexity is the cost you pay in terms of belief updating. It's literally that measure of movement from the prior to the posterior. That costs energy via the Zielinski equality, which means if you use the wrong kind of overly parameterized generative model, say with 1 billion parameters in a state-of-the-art deep learning network, you are doing it in the statistically least optimal way and using a massive amount of electricity. So another way of stating that is that the direction of travel in machine learning, in particular deep learning, is exactly the wrong direction because it relies upon big data and overly parameterized, overly complex generative models. So I'm hoping that active inference and the free energy principle will reverse that direction of travel through proof of principle. So what we have instead now is not throwing billions of data points at your deep learning machine and millions of dollars to a team of engineers who are trying to handcraft and tune the parameters of their particular variational autoencoder or long short-term memory layers in a convolutional network. Instead, you will let the machine itself decide what is the most informative data it needs to resolve its uncertainty. It will run either on an edge computing device, but it's certainly running your laptop, and it should finish and converge within minutes to days as opposed to days to months, and it will cost you $100 or even $10 as opposed to $1 million. So I'm deliberately completely overstating the benefits, but that reversal of direction of travel is mathematically obvious. It hits you in the face when you start to sort of articulate computation and intelligence in terms of the process of inference, and just look at the underlying maths in terms of the information geometry, and then using things like the Zielinski equality to understand that in terms of both the computational cost, but also the thermodynamic cost of computation. So I think that's going to be, in principle, I'm sure I'm completely wrong. I'm probably talking complete rubbish, but in my little fantasy world, data mining is a thing of the past. You won't need data farms because instead of going for mining big data, these curious machines will go and mine just the sparse data they need to resolve their uncertainty for what they are, for the context in which they operate. So we'll see a move to edge computing with sparse data, but it will be Bayes optimal. In a sense, it's just returning to the basic principles of optimal Bayesian design established in the 1950s by people like David Lindley, sort of revisited by people like David Mackay in terms of active learning in the 1990s, and then apparently completely forgotten about until the active inference movement or pushback against the direction of travel in sort of standard deep learning approaches, or even reinforcement learning without the curiosity.
Wow. It's incredible to think about all of the avenues that this has the potential to expand with. Well, I mean, I don't know what to say, Karl. You've been so generous. I mean, more than generous with your time, and I consider it a great privilege and honor that you have given me over 3 hours of your time to explain this. That's quite the gift, and I greatly appreciate that. Is there any final comments that you want to say, or anything that you want to summarize, or anything like that? And then also,
I'm very impressed with your stamina, and also the patience with which you ask your questions. Wait for about 20 minutes for a semblance of an answer. That is quite remarkable. So thank you very much.
No, the pleasure is all mine. You have been very, very generous, and I am quite sure that listeners will be very, very thrilled to hear all of your wonderful work that you've been doing. And so can't say enough thanks. Appreciate it.